For years, astronomers thought they had a solid picture of what the universe looked like in its earliest chapters. Tiny, messy clouds of gas, small clusters of newborn stars, nothing organized, nothing heavy, nothing resembling the galaxies we see around us today. Then James Webb started sending back its deepest observations, and suddenly that tidy story fell apart. In the first 2 years of data, scientists began spotting galaxies that looked far too grown up for their age, some appearing only a few 100 million years after the Big Bang, yet carrying the mass, brightness, and chemical richness of systems that should have taken billions of years to build. Webb even found objects structured enough to resemble early spirals, and hundreds of ultra-bright candidates that don't fit any familiar category. If these results hold, they don't just tweak our understanding of early cosmic history. They challenge the basic timelines we've relied on for how matter clumped together, how stars formed, how fast galaxies could assemble, and how complex the universe could become in such a short span of time. So today, we're going to unpack what Webb actually found, what makes these discoveries so uncomfortable for current models, and what possibilities scientists are starting to consider. Because something in those early snapshots isn't lining up, and whatever the explanation is, it's going to reshape our idea of how quickly the universe learned to build structure. If you want to understand why Webb keeps turning up surprises, it helps to know what makes it so different from anything we've ever put in space. People usually describe it as the most powerful telescope ever built, which is true, but that phrase hides the real reason it's rewriting entire chapters of cosmology. Webb was built specifically to see the universe at wavelengths where the earliest galaxies are actually visible. That sounds obvious, but it wasn't. When astronomers first started planning Webb in the late 1990s and early 2000s, the main question was how to design a telescope that could see far enough back in time to catch the first stars switching on. The key detail is that light from extremely distant objects doesn't just travel a long time. It gets stretched by the expansion of the universe. A burst of ultraviolet or visible light released shortly after the Big Bang arrives today stretched all the way into the infrared. Telescopes like Hubble simply weren't built to pick up most of that infrared glow. Even when Hubble pushed its instruments as far as they could go, it was detecting faint hints and rough shapes, not the full picture. Webb was engineered to fill that gap. The entire mission revolves around infrared performance. That's why its huge primary mirror looks gold. The coating boosts reflectivity in the infrared range. It's also why the telescope operates at extremely cold temperatures. If Webb were warm, it would glow in the infrared and blind itself. The sunshield, roughly the size of a tennis court, exists almost entirely so the instruments can cool down enough to detect these ancient, stretched-out photons. When astronomers talk about Webb being sensitive, they mean it can register signals that are barely above the natural thermal noise of deep space. To make that sensitivity useful, the mission includes instruments built for different types of infrared work. There's NIRCAM, which handles near-infrared imaging with extremely high resolution. There's NIRSpec, which breaks light into spectra, letting scientists measure distances, temperatures, chemical fingerprints, and motion. Then there's MIRI, covering the mid-infrared range where colder dust and faint older stars show up. Together, these tools let Webb capture not just pictures, but physical information about galaxies that existed when the universe was a tiny fraction of its current age. This combination of cold operation, large mirror area, and precise infrared instruments is why Webb can see galaxies at redshifts above 12 and 13, meaning we're looking at light emitted when the universe was less than 400 million years old. For context, if the entire 13.8 billion year history of the universe were compressed into a single human lifetime, Webb is letting us watch events from before the universe turned 4 months old. Nothing else could do that. There's another part of this story that often gets skipped. Webb doesn't just see farther, it sees in sharper detail at those distances. The larger the mirror, the smaller the patch of sky each pixel corresponds to, and the better the telescope can separate fine structure from blur. At these distances, Hubble's view tends to smear clumps of stars together into a vague glow. Webb resolves individual knots of star formation, clumpy regions of dust, and distinct pockets of gas. That extra clarity is exactly what allowed astronomers to spot early disks, compact but massive stellar populations, and chemical signatures that shouldn't be present so early in cosmic history. The payoff became immediately obvious in the summer of 2022. right after Webb released its first deep-field image. Astronomers were expecting to find faint, barely structured galaxies, specks that matched simulations of the early cosmic dawn. Instead, in that very first image, several dots were showing brightness and estimated masses that didn't line up with any common model. Nobody was ready to make bold claims yet. Early redshift estimates can be misleading, and sometimes bright objects turn out to be dusty galaxies much closer than they appear. But as more data came in, the pattern didn't go away. The telescope kept revealing galaxies that seemed too big, too bright, or too chemically mature for their supposed ages. This is the key point. Webb isn't breaking physics. It's revealing details that were always there but invisible to our previous tools. The universe didn't suddenly become more surprising in 2022. We finally built something capable of seeing what earlier telescopes flattened into indistinct blobs. And to be clear, the mission isn't only about looking far back in time. Webb is also studying exoplanet atmospheres, mapping star-forming regions in the Milky Way, and tracking chemical cycles in other galaxies. But the early universe work is where the shock factor has been strongest. Astronomy has always had a basic expectation that complexity takes time to build. Stars form, blow up, seed space with heavier elements, and only after many cycles do galaxies start looking well organized. Webb's images and spectra, sensitive to even small amounts of those heavier elements, keep suggesting that this buildup may have happened much faster than expected. Another reason Webb keeps finding anomalies is that it can collect extremely accurate spectra from objects that look like faint pinpoints. Spectra are how astronomers calculate redshift precisely. When Webb identifies a galaxy with a redshift like 13 or 14, that's not a guess based on color, it's based on clear spectral lines. These lines show which elements are present, how fast the galaxy is moving, how old the stars might be, and how much dust is in the system. Before Webb, most early universe candidates were color-selected, meaning researchers were estimating distances indirectly. Now scientists can measure them directly, which removes huge uncertainties that used to blur the picture. The ability to distinguish between genuinely early galaxies and deceptively bright imposters has tightened interpretations dramatically, and surprisingly, many of the brightest, most puzzling sources have held up under this closer inspection. Some early candidates have turned out to be somewhat nearer than first thought, but a significant number really do sit at those extreme distances. That's why these results have become so central to current debates. They're not based on one-off blurry detections. They're based on clean, well-measured spectra taken by a telescope built for exactly this purpose. The other major advantage Webb brings is its field of view. It can observe wide swathes of sky at incredible depth. The early universe studies aren't coming from one tiny patch. They're coming from large mosaics assembled over many hours. That improves statistics and reduces the chance that we're being fooled by rare gravitational lensing events or oddities found in small regions. The fact that Webb is finding these massive, luminous or chemically mature galaxies across multiple fields strengthens the argument that something fundamental may need to be rethought. All of this contributes to why Webb's results feel disruptive. Every improvement in instrumentation in the past century has extended our cosmic horizon a bit, but Webb is orders of magnitude better at seeing the universe in the wavelength range that actually carries early universe information. It's a little like switching from a dim flashlight in a foggy room to high-definition night vision goggles. The sudden jump in clarity means features that were previously invisible now show up everywhere. The telescope's vantage point also matters. Webb sits about 1 million miles from Earth at a point called L2, which gives it an uninterrupted view of deep space without the thermal and orbital interference you'd get if it were closer. This stable environment allows long-duration exposures, sometimes dozens of hours, which are necessary to detect faint signatures from galaxies that formed when the universe was still packed with opaque hydrogen clouds. Long exposures also reduce noise and help identify objects that would otherwise get lost in the background glow. While Webb isn't the first infrared telescope, it's the first that combines a giant mirror, extreme sensitivity, fine resolution, advanced spectrographs, and a stable deep space orbit. Earlier missions like Spitzer operated in the infrared but had much smaller mirrors, producing lower resolution. They could detect warm dust and nearby exoplanets, but not the first galaxies. Herschel saw further into the far infrared but didn't have the necessary resolving power. Webb is the first time all of these capabilities have been bundled together in a way that directly targets the earliest structures the universe ever formed. Something else that makes Webb particularly important is how well it works with other telescopes. It doesn't replace Hubble. It builds on Hubble's foundation. Hubble provides optical views of these regions, revealing structures and colors that Webb can't see. Meanwhile, ground-based observatories like ALMA pick up millimeter-wave signals from dust and cold gas. When you combine data from all three, you get a more complete physical picture of each galaxy. Webb is the missing infrared piece that ties these layers together. Without it, our view is incomplete, and some structures simply fell between the cracks. Now, with this missing piece filled in, we're seeing that many early galaxies are far more organized or massive than the previous picture ever suggested. This is where the confusion begins. The telescope is doing exactly what it was designed to do, reveal the earliest stages of cosmic history in clear detail. But the better the picture becomes, the more it seems that the early universe was not the slow, gradual builder that many models predicted. Instead, the cosmos might have been capable of forming large, bright, chemically evolved systems with surprising speed. Scientists don't all agree on what that means yet, but Webb's instruments have made one thing obvious. The early universe was more dynamic, more efficient, and more complex than the standard timeline assumed. We also have to consider how Webb's deep observations influence the statistics astronomers use. Earlier surveys often covered narrow fields, so one or two odd objects might be dismissed as rare outliers. But Webb's wide-field programs show that these mature-looking early galaxies aren't isolated cases. They appear frequently enough that they could represent a common stage of early galaxy evolution, not an exception. This raises questions about how matter behaved when the universe was extremely young. Did gas cool faster than expected? Did dark matter halos grow more rapidly? Were the first stars more massive or more efficient at seeding later generations with metals? These are open questions, and Webb's data is driving entire teams to rerun simulations, tweak physics models, and reevaluate long-held assumptions. What's remarkable is that Webb is still early in its mission. Its first few years have already forced astronomers to update redshift records, rethink chemical evolution timelines, and question long-standing predictions about how much structure the universe should have at different ages. And the telescope is only going deeper and wider each year. The next releases will likely reveal even more extreme objects, galaxies or black hole candidates that push our understanding further. Not because the universe is misbehaving, but because we finally built an instrument capable of seeing it as it really was. Fundamentally, Webb is a time machine. It's the closest humanity has come to observing our own origins on a cosmic scale. And while every major telescope has rewritten parts of astronomy, Webb may be the first to challenge basic narratives about how fast the universe organized itself. It's showing us that the early cosmos wasn't just flickering to life. It was building things at a pace we didn't expect and, frankly, didn't think was possible. Those capabilities are why the telescope keeps surprising scientists, and it's those very strengths, deep infrared sensitivity, fine spectral precision, large area imaging, and exceptional resolution that set the stage for the unexpected discoveries we're about to dive into next. Before Webb began returning those strange results, astronomers had a fairly stable picture of how the universe's first few 100 million years unfolded. This model wasn't built on guesses. It grew from decades of theory, observations from earlier telescopes, simulations run on supercomputers, and a huge amount of data about how galaxies evolve over billions of years. Even today, the broad framework hasn't been thrown out, but what Webb is revealing sits right at the edge of where those expectations start to break down. So let's walk through the version of early cosmic history most astronomers were working with before Webb surprised everyone. Because once you understand what the early universe should have looked like, the shock behind Webb's discoveries becomes much clearer. When we talk about the early universe, there are a few distinct stages. Right after the Big Bang, there's the hot plasma era. Too dense, too bright, too uniform for anything like stars or galaxies to exist. Then there's a cooling period as the universe expands. Roughly 380,000 years after the Big Bang, the universe becomes transparent, and the cosmic microwave background forms. After that, the first dark ages begin. Space isn't literally dark everywhere, but there are no stars yet, and most matter is neutral hydrogen. Light doesn't travel easily through this fog, and the universe at that stage is incredibly simple. No metals, no dust, no heavy elements, no planets, and certainly no spirals or giant galaxies. In this early framework, everything starts with tiny differences, slight overdensities in that otherwise smooth sea of hydrogen. These overdense pockets form because the early universe wasn't perfectly uniform. Some regions had a tiny bit more matter than others. Gravity slowly amplified those differences, and over thousands of generations of small changes, these regions grew dense enough to begin pulling in more gas. That process created the first dark matter halos, invisible scaffolds that eventually became the seeds of galaxies. The key word here is slowly. Under the standard model, nothing about this early growth process should happen quickly. The universe is expanding, gas is cooling only gradually, and everything is limited by how fast gravity can pull distant particles together. So even though the first halos form relatively early, they're small. Think of them as clumps that would eventually merge into bigger structures. In the theory, this sequence, small things building up into larger ones, is called hierarchical formation, and it's one of the pillars of modern cosmology. By about 100 to 200 million years after the Big Bang, simulations suggest that some of those halos should be dense enough to form the very first stars. The so-called population 3 stars. These are hypothetical. We've never observed them directly, mostly because they would have burned out billions of years ago, but we have strong reasons to believe they existed. They would have been made entirely from hydrogen and helium, with none of the heavier elements that later stars carry. Because of that lack of heavy elements, they were expected to be enormous, hundreds of times the mass of the Sun, and extremely short-lived. They burned hot, died fast, and ended as tremendous supernovae that spread the first heavy elements into the surrounding gas. This early enrichment event is important. Without heavy elements, gas doesn't cool efficiently, and cooling is what allows clouds to collapse and form new stars. So the first supernova explosions essentially kick-started the next wave of star formation. But again, in the standard picture, this enrichment happens in small pockets and takes time to spread. Maybe tens of millions of years, more likely hundreds of millions. The early universe is huge, and even energetic explosions don't reach far. Because of that, astronomers expected the earliest observable galaxies, the ones we might see with a telescope like Webb, to be tiny, simple, chaotic blobs. Nothing structured, nothing smooth, nothing that resembles the organized spirals and massive ellipticals we see today. These early galaxies should contain mostly young stars that formed recently, with just a trace of heavier elements from the earliest supernova. Their total mass should be small, maybe 1/100th of the Milky Way, or even less. And their light should come mainly from hot, young stars without much dust around them. This timeline doesn't come from just one model, it's the product of an enormous amount of cross-checking. Observations from Hubble match this picture fairly well. When Hubble looked deep into space, the galaxies it picked up near the cosmic dawn were usually faint specks, irregular in shape and low in mass. They looked exactly like the early stages of galaxy formation that simulations predicted. Scientists expected Webb to refine this picture and fill in some missing details, not overturn the foundation. Another major assumption was the rate at which galaxies could grow. Gas needs to flow into halos for stars to form, but gas doesn't fall in freely. It heats up as it collapses, and hot gas doesn't create stars until it cools. In the early universe, cooling was slow. That added another limit. Even if gravity was ready to build a big galaxy, the gas wouldn't cooperate quickly enough. So the early universe should have produced star-forming systems, but at a slow and steady pace. Enough to gradually brighten the cosmic landscape, but nowhere near fast enough to generate giant, organized galaxies within the first few 100 million years. Another part of this picture comes from observations of the later universe, the stages we can see clearly with existing telescopes. When astronomers look at galaxies across different epochs, they see a clear pattern. Young galaxies are messy. They collide often. They form stars in bursts. They aren't well organized until much later. Structured spirals like the Milky Way tend to appear several billion years after the Big Bang, not a few 100 million. The idea that a full spiral or a chemically mature disk could show up right at the start simply wasn't on the table. There's also the question of metals. In astronomy, metals means anything heavier than helium. The early universe shouldn't have many. Heavy elements form inside stars and get spread by supernova. That means every generation of stars enriches the next. The earliest galaxies should therefore be metal poor. Not because the physics demands it, but because there simply hasn't been time for enough star cycles to occur. If you only have a few 100 million years to work with, and each massive star takes millions of years to form, live, and die, the number of enrichment cycles is very limited. That should keep early galaxies chemically primitive. This chemical timeline isn't just a theory. We see clear evidence of it in older galaxies. When astronomers measure the light from distant systems, they can work out the abundance of oxygen, carbon, neon, and other elements. Galaxies at later stages in the universe have higher metallicity because they've lived through many generations of stars. That trend is so strong and so consistent that it became a standard tool for estimating the age and maturity of galaxies. If a galaxy has a lot of heavy elements, it almost certainly formed relatively late in cosmic history, not early. Simulations back this up as well. When scientists run large-scale cosmological models on supercomputers, the virtual universes they generate tend to produce the same trend. Small, primitive galaxies form first. Bigger, more chemically enriched ones come later. Anytime simulations produced galaxies that were too big, too early, something was assumed to be off with the physics inputs. Adjusting cooling rates, star formation efficiency, feedback strength, and gas inflow models always brought the virtual universe back into line with the expected timeline. Everything pointed toward a slow, orderly build-up of structure. Another factor shaping these expectations was the difficulty of assembling a huge number of stars in such a short amount of time. Even if you could build a massive halo early on, turning that raw material into stars requires raw speed. Star formation isn't instantaneous. It relies on cloud collapse, fragmentation, turbulence, feedback from nearby newborn stars, and a whole chain of hydrodynamic processes that all take time. There's a physical limit to how fast gas can collapse without blowing itself apart or choking off the forming stars with radiation pressure. Under normal assumptions, that limit should prevent early galaxies from reaching the masses that Webb is now reporting. Then there's the issue of reionization. This is the era when the first stars and galaxies emitted enough ultraviolet light to strip electrons off hydrogen atoms across the universe. Reionization was a major turning point because it changed how light could travel. But the timing of reionization gives strong hints about how many stars existed at early times and how bright they were. Measurements from telescopes observing distant quasars and the cosmic microwave background suggested that reionization unfolded between about 400 million and 1 billion years after the Big Bang. That timeline fits nicely with the idea that early galaxies were modest. If the universe had been filled with giant, bright galaxies extremely early, reionization would have happened much sooner than the data suggests. So, putting all of this together, the physics of gas cooling, the expected star formation rates, the hierarchical model of structure formation, the metallicity timeline, the reionization constraints, and the observations from Hubble. Astronomers went into the Webb era expecting to see a universe dominated by small, irregular, chemically simple galaxies. The earlier systems would be faint smudges, hard to detect even with infrared instruments. Maybe we'd catch the very first generation of stars indirectly. Maybe we'd fill in some missing gaps between the first clusters and the first recognizable galaxies. But nobody expected to see objects that looked mature. This isn't because scientists lacked imagination. It's because all of the available evidence, observational, theoretical, and computational, converged on one picture. The early universe was supposed to look like the first rough draft of galaxy formation, not the finished pages. The messy, clumpy, small galaxy era was seen as the foundation on which everything else was built. And that's what makes Webb's discoveries so unsettling. When a telescope finds one weird object, scientists can call it an outlier. When it finds several, the theory might need tweaking. But when it consistently reveals galaxies that appear far too luminous, far too massive, or far too chemically advanced for their place in the timeline, that's a signal that something fundamental in our assumptions may be off. Now, it's not that the early universe didn't go through all the stages we expected. It's that these stages might have been compressed, accelerated, or more chaotic than anyone predicted. The textbook picture, simple, slow, primitive, may have captured the broad strokes correctly but missed the speed and efficiency with which the earliest galaxies assembled themselves. To understand the real tension, you have to hold this expected image in your mind: tiny halos, limited enrichment, slow cooling, gradual star formation, no big structures, no spirals, and no massive galaxy clusters anywhere near the cosmic dawn. That's the model the scientific community was using as the baseline, and that's exactly the model that Webb's discoveries are now putting under pressure. When JWST started peering deep into space and far back in time, astronomers expected to mostly confirm the small, irregular, faint early galaxies. Instead, many of the early candidates turned out to be far more massive, brighter, and in some cases even structurally more evolved than theory suggested they should be. One of the earliest shocking discoveries was a galaxy called JD's GSZ 14-0. Spectroscopic data place it at extremely high redshift, meaning it existed when the universe was very young, yet it's surprisingly bright and compact. According to researchers, its luminosity appears to come from stars rather than from an active black hole, making it strong evidence that large, massive galaxies could form rapidly in the early universe. That goes sharply against prior expectations. Back then, such massive, dense systems should have needed far more time to assemble than the young universe had allowed. It's not just one or two oddballs. Surveys based on JWST data have identified a population of galaxies in the early universe that appear more massive and more numerous than predicted. A study found a significantly larger number of what looked like ultramassive early galaxies than standard cosmological models had allowed for that early. This suggests that if taken at face value, the early universe might have produced many more massive galaxies, and more quickly, than our old playbooks said should have happened. Some of them would have had to convert gas into stars at a far higher efficiency than the galaxies we see nearby. Because the initial concern, these galaxies are too massive too soon, was so strong, scientists revisited their assumptions. For some of the overmassive early galaxies, the brightness didn't come purely from starlight but arose from other sources, in many cases from gas falling onto supermassive black holes. This accretion process produces light, especially in the infrared, which can make a galaxy look brighter and hence more massive than it really is in stars. When astronomers excluded such little red dots, compact, red, bright early galaxies likely dominated by black hole accretion, the remaining population looked more compatible with predictions. In other words, some of the biggest violations of expectations may result from misattributing brightness to stars rather than black holes. But even after that correction, there remain more massive than expected early galaxies than models predict, though not as extreme or as numerous as earlier feared. Beyond mass and brightness, JWST has started to reveal surprisingly complex characteristics in some early galaxies. The early favorite picture was that of small, simple, metal-poor galaxies, the first stars forming out of almost pure hydrogen and helium. Yet in cases like JD's GSZ 14-0, the galaxy's brightness and size hint at rapid star formation and hence fairly quick chemical enrichment. That implies more generations of stars forming and dying than previously assumed possible within a few 100 million years, which would dump heavier elements, metals in astronomy parlance, into the gas, enabling cooler, more efficient star formation sooner than predicted. Not every early universe object is a too mature galaxy. Recent work surveying more than 250 galaxies from when the universe was about 800 million to 1.5 billion years old found that most of them remain highly turbulent, disordered, and clumpy, consistent with traditional expectations for early galaxy formation. Rather than smooth rotating disks, these galaxies had chaotic gas movement, messy star-forming regions, and little sign of the kind of ordering you see in mature galaxies. So the truth seems to be, the early universe was more diverse than expected. Some galaxies remained small, chaotic, and primitive, while others became unexpectedly massive, bright, and perhaps chemically advanced. To explain how some early galaxies became so massive so fast, scientists have proposed that star formation in the early universe was unusually efficient compared with today. In a denser environment, gas could collapse more readily, and because dust, which blocks or dims light, was likely less abundant, galaxies might appear brighter or form stars more efficiently. One proposed factor: with less dust, starlight escapes more easily, making galaxies appear brighter. Also, early galaxies may not hold onto their dust. Intense radiation pressure from many massive young stars could blow out dust quickly, reducing attenuation and making these galaxies unusually luminous in infrared. Finally, feedback processes that slow star formation in modern galaxies, like heating by supernova or active galactic nuclei, might have been less effective or differently tuned in the early universe, allowing faster accumulation of stellar mass than expected. Now that we've laid out what JWST is seeing, here's why these findings unsettle the expected model of early cosmic history. The biggest tension is one of timescales. The standard cosmological model, often referred to as lambda cold dark matter, predicts that structure formation proceeds hierarchically and slowly. Small dark matter halos accumulate gas, form a few stars, merge over time, gradually building up larger galaxies. Given the rate of these processes and the time available just a few 100 million years after the Big Bang, it was not considered possible for a galaxy to become as massive or as bright in stars as some of the JWST sources appear to be. If a galaxy like JD's GS Z14-0 truly formed so early and produced a large stellar mass, that implies extremely rapid, efficient star formation, or some other physical process we didn't anticipate. Even after accounting for possible biases, e.g. black hole brightness being mistaken for starlight, observations still suggest there are more massive early galaxies than expected. That means either our simulations underestimate how fast and how often galaxies can grow early on, or they miss key physics that accelerate formation. If early galaxies achieved high masses quickly, they must have gone through many cycles of star formation and death, generating heavy elements and dust. That runs counter to the expectation that the first galaxies should be metal-poor, primordial systems with very simple chemical compositions. The apparent brightness and density suggest a faster-than-expected enrichment process. The combination of wildly different galaxy types in the early universe, from chaotic, small, clumpy systems to bright, massive, compact ones, suggests that a single uniform model may not be adequate. Instead of a smooth progression, the early universe may have been much more varied depending on local conditions: gas density, environment, dark matter, halo mass, feedback strength, dust content, etc. This undermines a key simplifying assumption in many simulations, that early galaxy formation follows a relatively predictable path, just scaled-down versions of later processes. Because the tension involves fundamental assumptions about how matter clumps under gravity, how fast stars can form, how gas cools and gets enriched, it touches upon the foundations of the standard cosmological framework. Some theoretical work suggests that if the observations hold up, we might need to reconsider aspects of the model. But as we'll see in the next chapters, there are also hypotheses that try to reconcile the data with standard cosmology, so the story is evolving, not yet definitive. Under lambda CDM, the prevailing cosmological model, structure formation is hierarchical and gradual. Small fluctuations in matter density grow under gravity, forming small halos, which gradually merge or accrete gas to build larger galaxies. But JWST has found galaxies at very high redshifts, i.e., very early times, with unexpectedly large stellar masses, too big to assemble within the short time available after the Big Bang. This has been framed as a time compression problem. The universe simply shouldn't be able to produce so many stars or such large systems so quickly under standard physics assumptions. In short, theory says, not enough time. Observations say, see for yourself. Stars form when gas clouds collapse under gravity, but collapse heats the gas. To form stable stars, gas needs to cool efficiently. In a primordial environment, early universe, gas lacks metals, heavy elements, that help cooling, so gas cooling should be inefficient, impeding rapid star formation. Even if stars begin forming, feedback effects, from supernova explosions, radiation pressure, stellar winds, tend to blow gas out, slowing down further star formation. That limits how quickly a galaxy can build up mass. Under these constraints, forming a massive, bright galaxy with large stellar mass, significant heavy element enrichment, and perhaps disk structure, within a few 100 million years seems physically implausible under lambda CDM assumptions. So even if you give the universe every favorable condition, gas availability, ideal density, The known physics of star formation and feedback seems to impose a hard speed limit that these early galaxies appear to violate. Theoretical models predict a steep drop in the number of massive galaxies as you go to higher redshift. The luminosity function, which tracks how many galaxies shine at a given brightness, should evolve quickly, fewer bright massive ones early on. Instead, JWST data show an excess, more massive or bright early galaxies than predicted. If these numbers hold up under more scrutiny, it suggests the early universe was far more efficient or active in building big galaxies than standard cosmological simulations allow. That mismatch matters deeply because cosmological models rely on matching observed distributions, mass, number, brightness, of galaxies across cosmic time. Under older models, informed by earlier telescopes like Hubble, disk galaxies and spirals were thought to emerge relatively late, after chaotic merging and gradual accumulation of mass. For a long time, the expectation was that early galaxies at high redshift would look irregular, disturbed, clumpy, not smooth disks or structured spirals. Yet recent observations using JWST indicate the presence of disk-like structures and even candidate spiral galaxies at redshifts where, according to theory, such morphology should be rare or impossible. That implies the processes leading to structural organization, angular momentum settling, gas inflow, disk formation must have operated much faster or more efficiently than expected. In short, it's not just mass or brightness that's surprising, it's the maturity of structure. The existence of large numbers of massive early galaxies also has implications for other cosmological observations, like the cosmic microwave background, CMB, and how matter clusters over time. Some studies argue these early massive objects would alter predictions for gravitational lensing of the CMB and challenge parameter fits based on CMB observations. That means if the early galaxy findings are real and widespread, they don't only break galaxy formation models, they might force a re-evaluation of parts of cosmology that were thought more secure. Some researchers take the observations at face value and suggest that perhaps our assumptions about early universe physics are incomplete. For example, maybe star formation was far more efficient, or feedback processes work differently. Others have gone further. Some suggest alternative theories of gravity rather than invoking dark matter, where structure could form more rapidly, a hypothesis revisited because of these early findings. A few even entertain more exotic ideas. Perhaps some of these early objects aren't normal galaxies, but are seeded by large primordial structures, e.g. early black holes or non-standard initial conditions, which could jumpstart galaxy formation. In short, if we take JWST at face value, science might need to rethink parts of how structure forms and evolves. Not a minor tweak, but a potential paradigm shift. Because these implications are so big, the scientific community is not falling on one side or the other. Instead, multiple lines of investigation and skepticism are active. Here's how researchers are responding. 1. Resolution. Some of the earliest candidates may look massive only because they are unusually luminous, possibly because of non-stellar contributions, like accreting supermassive black holes, active galactic nuclei, which produce lots of light as gas falls onto them. When such objects, sometimes called little red dots, are excluded, the remainder of early galaxies observed by JWST fall more comfortably within the predictions of lambda CDM, although there remain more of them than expected. So part of the impossible early galaxy problem might be diminished once we correct for non-stellar light. Another possibility: conditions in the early universe might have allowed for far more efficient conversion of gas into stars. Higher ambient densities, faster cooling, perhaps aided by early generation processes, or weaker feedback might have allowed galaxies to build up mass rapidly. If that's the case, then our models for star formation, often calibrated to local shocked universe today conditions, may underestimate what's possible in the first few 100 million years after the Big Bang. Some scientists revisit older alternative cosmologies. For example, modified Newtonian dynamics, MOND, proposed originally as an alternative to dark matter, predicted much more rapid structure formation in the early universe. Some proponents argue that JWST's observations align better with these predictions than with LCDM. Other more speculative proposals include adjustments to cosmological expansion history or exotic early universe physics that changes how structures form at high redshift. Recent work has attempted to simulate alternate cosmologies or altered physics, e.g. different dark energy behavior, modified gravity, or non-standard initial conditions, to test whether they produce the large mass, high luminosity early galaxies seen by JWST, and in some cases they can without breaking the successes of standard cosmology at later times. This branch of research is promising because it demonstrates that the observations don't automatically force a rejection of all existing theory, but rather point to possible refinements or extensions. A major caveat: many of the early high redshift candidates come from photometric redshifts, estimates based on color, which can be uncertain. Until more of these get confirmed via spectroscopy, which gives precise distance and physical data, some may turn out to be less distant or have properties different than initially estimated. Also, the brightest, most massive galaxies are easier to detect at extreme distances that may bias observations. The faint, small or normal early galaxies may still be there, but harder to spot. This selection bias means the sample might not be representative of the entire population. Because of all these, many researchers emphasize caution. Extraordinary claims, like galaxies too mature too early, require extraordinary and robust evidence. As one team put it, after corrections, some early galaxies are less extreme, but even with those corrections, there remain more massive early systems than the simplest models predict. This tension between observation and theory isn't a trivial detail. It strikes at the heart of how we believe the universe evolved. If the early universe could build massive, structured, chemically enriched galaxies so fast, then our understanding of star formation, the physics of how gas collapses, cools and turns into stars, might need major revision. The timing and role of heavy element, metal enrichment changes. Earlier enrichment means dust, cooling, and galaxy evolution might work differently than thought. Predictions from cosmological simulations on galaxy distribution, evolution, and number densities over time may be incomplete or missing key physics. Even fundamental assumptions, like how matter clumps under gravity or the role and behavior of dark matter/energy, may need re-evaluation or enlargement with modified theories. The story of cosmic history, how the universe went from smooth after the Big Bang to structured today, might have been faster, messier, more varied than the textbook narrative suggests. In short, what Webb is showing suggests the early universe might be more dynamic and complex than our simplified models allowed. Below, I list the 5 clearest ways Webb's early results strained theoretical expectations, explain why each is a headache, and then judge whether it's probably fixable by tweaking messy astrophysics, or whether it would demand a deeper change to cosmology. Where useful, I also give concrete observational tests that would help settle each issue. Several JWST-identified objects have spectroscopic conformations, placing them less than a few hundred million years after the Big Bang. Yet they show luminosities and inferred stellar masses that, if that light is mostly starlight, imply formation of hundreds of millions of solar masses of stars in an implausibly short time. That directly contradicts the standard hierarchical picture where small halos form first and large stellar masses build up slowly through accretion and mergers. Basic physics limits how fast gas can collapse and convert into stars. Cooling rates, pressure support, and feedback from the first generations of stars and supernovae all slow further star formation. Under lambda CDM, there simply isn't enough time for many halos to reach those stellar masses that early, unless star formation is orders of magnitude more efficient than our models assume. Photometric/spectroscopic misestimates and observational bias. A subset of the early candidates were initially photometric and later revised. Spectroscopy has corrected some redshifts and lowered some mass estimates. Observational misclassification, e.g. confusing AGN emission lines or strong nebula lines with stellar continua, could inflate inferred stellar masses. This is partly resolved as more spectra arrive, non-stellar light contamination. If accreting black holes, AGN, or unusually strong nebular emission lines dominate the infrared flux, the stellar mass estimate is biased high. Removing AGN-dominated sources reduces tension substantially. Top-heavy initial mass function, IMF, or bursty star formation. If the earlier stars were systematically more massive, a top-heavy IMF, they would be brighter per unit mass, making a system appear more massive than the actual stellar mass. Rapid, bursty star formation episodes could also create short-lived brightness spikes that mislead mass estimates. Many in the field treat this as a calibration and interpretation problem that will become clearer as spectroscopy accumulates. If after robust spectroscopic confirmation a large population still shows implausible stellar masses, then the field will have to consider more radical physics. Secure spectroscopic redshifts for large samples, deep NIRSPECC/MIRI spectra to separate stellar continuum from emission lines, and AGN signatures. ALMA observations for cold gas and dust mass to cross-check mass budgets. Spectroscopy from JWST has detected oxygen and other metal emission lines in galaxies that exist when the universe is only a few hundred million years old. That implies several generations of massive stars already formed and exploded, enriching the gas far earlier than simple timelines predict. Metals are forged in stars and dispersed by supernova. Reaching detectable metallicities requires not just the first stars, but multiple cycles of star formation and feedback. In the standard picture, there hasn't been enough time for widespread metal enrichment of that level across a galaxy. Patchy enrichment and observational selection. We might be selectively picking out the rare, overdense regions that enriched earlier than average. JWST's sensitivity could bias us toward unusually evolved pockets. Massive, short-lived population 3 stars. If the first stars were extremely massive and short-lived, they would enrich gas quickly. This is still standard astrophysics, just pushed to extremes of efficiency. Revised models for metal mixing and cooling. Early metal transport could be faster or more localized than many simulations assume. If small early halos efficiently pollute their immediate environments, then locally high metallicities are possible. Rapid enrichment can plausibly be accommodated by plausible, but currently uncertain, variations in early stellar populations and enrichment chart mixing efficiencies. The detection does push models to include faster metal dispersal and possibly different IMF assumptions. Measure metallicities across many sightlines in the same early field. Use spatially resolved spectroscopy, NIR-SPEC IFU, and ALMA to map metals versus. Dust. Search for population 3 signatures, very specific spectral features that would argue for extremely massive first stars. Several surveys and teams report an apparent excess of bright candidate high Z objects compared with the number densities predicted by most lambda CDM-based galaxy formation simulations. Recent claims include many dozens to hundreds of unusually luminous early candidates in some fields. Cosmological simulations tuned to reproduce the low redshift universe predict a steep drop-off in the number of bright galaxies as you move to earlier times. An overabundance means the early universe produced luminous objects more efficiently or more commonly than the models allow. Selection effects and cosmic variance. Deep JWST fields are tiny patches of sky. If we happen to look at cosmic overdense sightlines, we'll overestimate the global abundance. Also, the surveys preferentially detect luminous outliers, making the sample non-representative. Photometric contamination. Photometric redshifts can be ambiguous. A fraction of candidates may be lower redshift interlopers or blended sources. Emission line boosting. Strong nebula lines can artificially inflate broadband fluxes used to estimate luminosity and mass, biasing the luminosity function. Many teams are already finding that after careful spectroscopic follow-up and accounting for AGN/line boosting, the tension shrinks. But if robust spectroscopic surveys continue to show a systematic excess across many independent fields, that would be harder to reconcile without changing assumptions about early baryonic physics or initial conditions. Larger multi-field JWST programs to beat cosmic variance, spectroscopic confirmation across multiple fields. Joint analyses combining JWST plus deep ground-based /ALMA data to model selection biases. Webb has produced images and kinematic data showing candidate disk-like and even spiral morphologies at epochs when theory expects chaotic, merger-dominated clumps. a grand design spiral appearing within approximately 1.5 billion years, or disk-like ordered rotation even earlier, would be surprising because gas-rich, violent early environments should destroy delicate spiral patterns. Building an ordered disk requires the system to settle angular momentum and avoid disruptive mergers long enough for rotation-supported structure to form. In lambda CDM, early epochs are merger-heavy and turbulent, so ordered morphology should be rare until later. Bias toward massive early halos that could stabilize disks. Massive, unusually quiet halos might form early in overdense regions and settle into disks faster than average. These would be rare but detectable with JWST's sensitivity, projection effects, and resolution limits. Some apparent spiral structure could be chance alignments, tidal features, or clumpy chains masquerading as a disk in 2D projection. Higher resolution kinematics, velocity maps, can settle whether a system is truly rotation-dominated. Rapid angular momentum acquisition in certain environments. Simulations with refined baryonic physics sometimes produce early disks if gas inflows carry coherent angular momentum. Morphological surprises often collapse under the weight of detailed kinematics and better data. If multiple independent velocity maps confirm fully mature, long-lived spiral arms extremely early and across many systems, that would be a much stronger challenge bordering on paradigm level. For now, careful kinematic follow-up is the right path. Resolved kinematic maps, NIRSPECIFU. Look for ordered rotation curves. Compare morphological classification with velocity support metrics. Deeper surveys to find whether such disks are common or rare. If the first four issues remain after exhausting observational and astrophysical explanations, the remaining possibility is that our basic cosmological framework, or its parameter values, is incomplete. That could mean changes in initial density fluctuation amplitude on small scales, non-standard dark matter properties, modified gravity at early times, or exotic early energy injections, any of which could accelerate structure formation. Some papers explicitly suggest that JWST's counts at Z greater than 10 create mild tension with LCDM expectations. Lambda CDM isn't just a model for galaxy growth, it's constrained by the cosmic microwave background, large-scale structure, and many other independent datasets. Changing it risks breaking those successes. Any modification must thread the needle, produce more early structure without wrecking agreement with CMB and later-era observables. Enhanced small-scale power in initial fluctuations. If the primordial power spectrum had extra power at small scales, halos could collapse earlier. This often conflicts with CMB constraints, so it's tightly constrained, warm or interacting dark matter variants. Some dark matter models alter halo assembly rates, but most variants slow structure formation, not speed it up. Primordial black holes or early seed mechanisms. Huge black hole seeds or other exotic collapsed objects could seed early galaxy growth, but they're speculative and tightly constrained observationally. Modified gravity or early dark energy behavior, changing the expansion or growth history, could in principle speed formation, but again would need to remain consistent with the CMB and BAO, baryon acoustic oscillations. Most researchers treat cosmology-level changes as a final resort after exhausting observational, selection, and baryonic physics explanations. If robust surveys across many independent fields show systemic, reproducible discrepancies with lambda CDM, then cosmology-level revisions become a live possibility. Cross-check JWST counts and properties against CMB-derived growth histories. Use independent probes, e.g., gravitational lensing, 21 cm cosmology when available, to measure small-scale power. Test for exotic early black hole populations with deep X-ray and radio observations. Observational/interpretation issues, photometric redshift errors, AGN contamination, emission line boosting. Most likely, early spectroscopic work already reduced extreme cases. Continued spectroscopy should further clarify. Astrophysical tweaks, higher star formation efficiency, top-heavy IMF, rapid enrichment. Plausible. These require updates to subgrid physics in simulations, but don't overthrow cosmology. Selection effects and cosmic variance. We looked where the rare extreme cases are. Very plausible. Larger area surveys will test this. Exotic seeding, primordial black holes, special early conditions. Possible but speculative. Would need multiple independent signatures beyond brightness, mass estimates. Fundamental cosmology change, modify lambda CDM. Least likely but highest impact. Only invoked if exhaustive astrophysical and observational fixes fail. Spectroscopic confirmations, the fastest path to clarity. If most extreme candidates are spectroscopically confirmed with stellar-dominated spectra, tensions grow. If many collapse into lower Z or AGN cases, tension eases. Kinematics and resolved metallicity maps. These will distinguish true mature disks and chemically evolved systems from imposters or localized enrichment. Multi-field statistics. Seeing the same excess across many independent sightlines would push us away from cosmic variance explanations toward real theoretical change. Right now, the community's stance is cautious curiosity. Webb has revealed phenomena we didn't fully anticipate, but most reasonable paths to resolution lie in improved data and refined astrophysical modeling. Only if those fail will the debate move from tweak the physics into rewriting cosmology. When a galaxy forms, it starts as a halo of dark matter, which doesn't shine, that gathers gas, mostly hydrogen and helium in the early universe. To turn that gas into stars, the gas must cool, condense, and collapse under gravity. But each of those steps comes with physical constraints. Below, I walk you through the main bottlenecks and why early massive galaxies are especially hard to build quickly. Gas clouds heat up as gravity compresses them. To collapse further and fragment into stars, they need to lose that heat via radiation. In the modern universe, heavy elements, metals, and dust make cooling much more efficient. Atoms with many electrons can radiate energy away. Molecular interactions can carry away heat. Dust can help, etc. But in the early universe, gas was largely metal-poor, only hydrogen and helium, so cooling was inefficient. Studies of extremely metal-poor galaxies in the nearby universe confirm that star formation is much less efficient under those conditions. Simulations that include realistic physics of metal cooling and feedback show that galaxy formation in low metallicity conditions tends to suppress early star formation and delay buildup of stellar mass. Because cooling is slow, gas remains hot and resistive to collapse, preventing rapid star formation. That puts a natural speed limit on how quickly a galaxy can build up mass. Even if a cloud starts collapsing, star formation doesn't proceed unimpeded. Once the first stars form, they strongly influence their surroundings. Massive stars emit intense ultraviolet radiation that can ionize gas, heating it. This makes further collapse harder because the gas resists gravity. Stellar winds and supernovae from these first stars inject energy and momentum into the surrounding gas, blowing it away or heating it. This reduces the amount of cold, dense gas available for forming new stars. As a result, star formation tends to self-regulate. If the rate of forming new stars surges, feedback increases, which slows or shuts off further formation. This principle, called feedback-regulated star formation, seems to apply in most galaxy formation models. In short, even under ideal conditions, plenty of gas, enough density, there's a speed limit set by feedback physics. Creating a massive population of stars quickly without blowing your gas away is very hard. Large-scale cosmological simulations and more focused zoom-in simulations of individual halos have repeatedly shown that converting the majority of a halo's gas into stars quickly is very inefficient. In many halos, only a small fraction of baryons normal matter ends up in stars. Even when metal cooling, gas accretion and feedback are all modeled carefully, the resulting star formation histories tend to spread out over time, not concentrate in a rapid early burst. Thus, for an early galaxy to assemble hundreds of millions of solar masses of stars within a few 100 million years, as some observations suggest, it would need to be far more efficient at converting gas to stars than simulations ever allow under standard physics. Massive star formation requires a large reservoir of cold, dense gas. The simplest way to get that is for a massive dark matter halo to accrete a lot of intergalactic gas early and keep it cold long enough to collapse. That's what standard models assume dark halos do over cosmic time. But observations of some early massive galaxies challenge that assumption. Some early massive galaxies observed with purported high stellar mass apparently contained very little cold gas or dust, which usually traces gas. For example, a study using ALMA found that several massive early galaxies had almost no dust continuum emission, which suggests their reservoirs of molecular gas, the fuel for star formation, were already greatly depleted or removed. If the gas is used up quickly, fast star formation, or blown out by feedback, then sustaining continued rapid growth becomes very difficult. That limits how much star formation can happen overall. This introduces a strong tension. You need a big, sustained gas supply to build a massive galaxy early, but if gas is consumed or removed too quickly, the window closes fast. The balancing act is hard to pull off under standard assumptions. Astronomers have tried pushing models to their limits to see whether early, rapid growth could happen. For example, some recent simulation studies suggest that under certain conditions, e.g., when stellar feedback fails to regulate star formation efficiently in massive halos at very high redshift, star formation efficiency could be higher than average. In other words, maybe in the densest early halos, gas inflow and collapse happened so quickly and feedback was less effective, allowing a rapid, early buildup of stellar mass. But even these optimistic runs tend to struggle to reproduce the most extreme early massive galaxy candidates, especially when counting how many such galaxies there are. That means even with stretched assumptions, high efficiency, fast collapse, favorable environment, forming many large galaxies early remains difficult, unless there's something we're missing. Because forming massive, bright, stellar-rich galaxies so early is so hard under standard physics, several possible explanations and consequences emerge. These aren't necessarily new physics, but they do demand serious rethinking of some of our assumptions. Perhaps standard assumptions, cooling rates, feedback strength, gas inflow, fragmentation, underestimate what could happen under the extreme conditions of the early universe. For example, the first generations of stars may have had a different initial mass function, IMF, favoring more massive stars, which would produce more light per unit mass and enrich the environment faster. This could accelerate cooling in subsequent generations. Theoretical studies have long considered the idea of a top-heavy IMF for early galaxies. Feedback mechanisms, radiation pressure, supernova might have been less effective or differently regulated in dense early halos, allowing gas to collapse quickly without being blown away, at least for a while. Gas inflow from the intergalactic medium might have been more efficient or more rapidly funneled into early massive halos than often assumed, providing a steady supply of fuel. If enough of these conditions align in just the right way, early rapid growth becomes more plausible. But it would require reframing parts of our astrophysical modelling, especially of early star formation. Another key possibility is that what we're seeing now with instruments like James Webb Space Telescope, JWST, are rare outliers, the exceptional, fastest developing galaxies, because they're the easiest to detect, brightest, most massive, most luminous. Dimmer or more modest early galaxies may simply be below our detection threshold. This introduces a strong observational bias. If that's the case, the average early galaxy may still follow the slow hierarchical growth path. The extreme objects being reported might represent special halos, rare, lucky regions where everything, gas supply, density, feedback suppression, aligned for rapid growth. As surveys expand to larger volumes and fainter detection limits, we may get a more representative sample of early galaxies, which could show that these too massive too soon cases are outliers, not the norm. This remains one of the more conservative and probable resolutions. In fact, some scientists argue that once selection effects and biases are fully accounted for, the tension with theory becomes more manageable. Maybe the conditions in the very early universe, the physics of cooling, the behavior of gas, the nature of early dark matter halos were sufficiently different from today plus standard assumptions that our models need revising. For example, metal enrichment from early massive stars could have happened faster than assumed, allowing efficient cooling earlier. That would accelerate the transition from primordial, metal-poor star formation to normal star formation. The interplay between dark matter halo assembly, gas inflow and baryonic physics in those early epochs might favor rapid mass accumulation under certain conditions, perhaps more common than we thought. There may be feedback mechanisms or gas dynamics processes in early galaxies that we don't yet model well. Turbulence, magnetic fields, cosmic rays, cold flows from cosmic Webb filaments that could speed up collapse and star formation under the right circumstances. If these are true, then the standard recipes for simulations might need updating, meaning cosmology remains intact, but astrophysical modeling gets richer and more complex. Because of all these uncertainties, scientists emphasize caution. Here's what still needs to be done: more spectroscopic confirmations. Many of the early high redshift galaxy candidates were initially identified by their colors, photometry, which is less precise and more prone to error. Spectroscopy reveals redshift more confidently and lets us study the physical properties, stars versus gas versus dust, more reliably. Better measurements of gas and dust content. To know how much fuel these galaxies had, we need observations, e.g. with ALMA or future instruments, of cold gas, molecular hydrogen tracers, dust continuum, to test whether a high stellar mass is plausible given the gas budget. Refined simulations with updated physics. Simulators need to test a range of conditions: high gas inflow, top-heavy IMF, efficient enrichment, varying feedback strength, to see whether extreme early growth is possible under realistic, physically consistent scenarios. Broader and deeper surveys. Observing larger, more representative volumes, not just the brightest rare galaxies, will help assess how common these early fast growers really are. If they're rare outliers, the tension is smaller. If they're common, that points to more systemic issues. The physics behind star formation, cooling, collapse, feedback, imposes strong constraints on how quickly galaxies can form. Under the conditions expected in the early universe, those constraints are severe. That's why early massive galaxy candidates from JWST are so provocative. They push against the speed limits of physics as we understand them. Yet, there are plausible paths forward. Maybe early galaxies were more efficient star factories than our present-day intuition suggests. Maybe our observational sample is strongly biased toward extraordinary cases, or maybe early conditions were more favorable to rapid growth. None of those options requires rewriting gravity or throwing away the Big Bang framework. But they do demand humility. We need better data, broader surveys, more nuanced simulations. For now, the timescale problem remains one of the strongest reasons to treat the earliest overmassive galaxy candidates with caution and curiosity. When James Webb's first deep observations came in, the headlines focused on the sheer number of bright, surprisingly well-organized galaxies showing up far earlier than expected. But before anyone could claim the universe was behaving in a way that shouldn't be possible, astronomers had to ask a harder question. Are these objects actually what they look like? Because when you stare this far back in time, mistakes are incredibly easy to make. You're dealing with faint signals, distorted by distance, filtered through dust, and stretched by cosmological redshift. Even the best telescope ever built has to work through those layers. So in this section, we're digging into what the data actually show, the methods astronomers use to confirm whether a distant object is real, and why so many scientists were cautious about the earliest claims. This matters for one reason. If these galaxies truly are as massive and mature as they appear, then something about the earliest chapter of cosmic evolution needs rewriting. But if they're not, if they're imposters masquerading as early giants, then the mystery shrinks. So let's break down how astronomers separate one from the other, and what happened case by case as Webb's detections were checked, challenged, and eventually strengthened. When astronomers look for early galaxies, they're mostly searching for a dropout pattern in the spectrum, a sudden dip in brightness at certain wavelengths caused by neutral hydrogen-absorbing light. The position of that dip tells us roughly how far away something is. This method works extremely well when hundreds or thousands of galaxies are involved. But for individual objects, especially very distant ones, it can be deceptive. A dusty galaxy at a slightly closer distance can mimic the colors of a pristine, young galaxy farther away. A compact starburst in the mid-range universe can look like a small, bright object from the first few 100 million years. Even a red, old elliptical galaxy sitting at moderate redshift can masquerade as a high redshift object if its dust and stellar populations happen to line up just right. And that's before we get into the trickiest cases: active galactic nuclei. A supermassive black hole feeding heavily can outshine an entire galaxy. If that point-like source happens to sit inside a small host, or if the host is too faint to see, observers can overestimate how much normal starlight is present and conclude they're looking at an enormous early galaxy when they're really looking at a black hole lighting up its surroundings. So from the very beginning, astronomers treated Webb's too big, too early candidates with healthy skepticism. Not because the detections looked suspicious, they didn't, but because interpreting these signals is a delicate business. And unless you get the distances right, everything else, mass, size, age, growth rate, collapses. Right after launch, some of the earliest analyses claimed galaxies that seemed almost absurdly massive. Tens or even hundreds of billions of solar masses less than 400 million years after the Big Bang. If those numbers were correct, it would mean that huge structures formed nearly instantaneously, far faster than any model predicted. Astronomers immediately raised red flags. Many of those claims were based on photometry alone. That's reliable for identifying a population of high redshift objects, but not for assigning precise ages or masses to individual ones. A few initial papers weren't careful about uncertainties, and that fueled headlines that exaggerated the tension with cosmology. But over the next year, teams went back, re-evaluated the data, applied more conservative modeling, and dropped many of those extreme mass estimates. Some objects that originally looked enormous turned out to be bright but lightweight, possibly dominated by young stars or black hole activity. Instead of finding dozens of impossibly massive galaxies, astronomers eventually narrowed the list down to a smaller set that still stood out as unusual, but not beyond all expectations. These survivors became the interesting cases, objects at redshifts. 10, 11, 12, and beyond that seemed to carry much more stellar mass than expected for their era. They weren't galaxy cluster-sized monsters, but they were still impressive, enough to challenge the standard timeline but not enough to collapse the entire framework. And that's exactly where the scientific process did its job. The initial excitement gave way to careful inspection. Only after the weaker candidates were filtered out did the genuine puzzles remain. To truly confirm how old an object is, astronomers use spectroscopy, splitting the light into its full spectrum to identify atomic fingerprints and pin down redshift precisely. This method removes most of the ambiguity that photometry struggles with, but spectroscopy is time-consuming, and Webb can only target so many objects at once. That means the earliest months of data relied heavily on photometric estimates, with spectroscopy coming later to test them. As the first spectroscopic follow-ups began to roll in, something surprising happened. Many of the early galaxies really were as far away as advertised. In some cases, the redshifts were even higher than the photometric estimates. That confirmed that Webb wasn't being fooled by dust or intermediate galaxies. The telescope was just seeing genuinely distant objects that previous observatories couldn't detect. This doesn't automatically confirm that these galaxies are too massive, because mass is harder to measure than distance. But it does confirm that the basic picture, bright, compact galaxies existing 300 to 500 million years after the Big Bang, is real. And that already pushes against earlier expectations. The more spectroscopy came in, the more confident astronomers became that many of these early objects truly live in the era where the universe was still transitioning out of its primordial state. Even if their masses get revised downward, their mere existence at such early times forces scientists to update how quickly early galaxies assemble and how fast the first stars enrich their environments. Distance is straightforward once you have a spectrum. Mass, on the other hand, is a chain of assumptions. To estimate how much stellar mass a galaxy has, astronomers look at its spectrum or its broadband colors and ask, what kind of stars with what ages and distributions would produce this light? That requires modeling star populations, accounting for how stars redden as they age, estimating how much dust is present, and guessing at the galaxy's history of star formation. But in the early universe, those assumptions are especially fragile. Here's why. First, very young galaxies can look deceptively bright. If you have a small number of incredibly massive newly formed stars, they put out a huge amount of light. That makes the galaxy seem larger and older than it is. Without knowing the detailed age of the stellar population, brightness alone can mislead. Second, the amount of dust is hard to determine at high redshift. Dust hides light from older stars and makes a galaxy look younger. If you assume too little dust, you overestimate the stellar mass. If you assume too much dust, you underestimate it. Webb helps here by observing infrared wavelengths, but even that can't perfectly pin down dust in the faintest distant targets. Third, the early universe may have had a different distribution of stellar masses, something astronomers call the initial mass function. If early star formation favored heavier stars more than present-day galaxies do, then models built for modern galaxies will misread those early ones. A few teams have already suggested that adjusting the IMF might eliminate the apparent tension. This doesn't guarantee that all early massive galaxies will shrink under better analysis, but it does mean that every mass estimate at redshifts 10 to 12 must be handled cautiously. Even small changes in assumptions can shift the mass by a factor of 2 or more. As the dust settled and the weaker candidates dropped away, several galaxies remained compelling outliers. These weren't the overhyped early monsters from the first month of data. These were carefully measured objects whose redshifts were secure, whose photometry was solid, and whose masses still looked surprisingly high. A few cases, after spectroscopy, confirmed that they're genuinely in the earliest 400 million years and that their brightness can't be explained away by dust or a single massive star cluster. These galaxies show structured, extended emission rather than a single-point source, which makes AGN contamination less likely. They show signs of chemical enrichment deeper than expected. And they display light profiles, suggesting they already had mature stellar populations. None of them individually breaks cosmology, but taken together they nudge the timeline in a direction that demands faster assembly, faster cooling, and faster star formation than the traditional picture allowed. These are the galaxies that keep theorists busy, not because they're impossible, they're not, but because they force us to adjust assumptions that have guided our thinking for decades. And they point toward a universe that was more efficient, more dynamic, and more rapidly structured than the quiet, slow-growth models many simulations were built around. A lot of the public conversation jumped straight to cosmology is broken. Scientists never took that seriously. There was no evidence that the large-scale structure of the universe, the expansion history, or the underlying framework needed rewriting. Instead, the serious questions landed squarely inside astrophysics: how fast galaxies should form, how effective cooling was under early conditions, how quickly the first generations of stars could enrich their surroundings, and how efficiently massive halos could convert gas into stars. The reason astronomers didn't panic is simple. Astrophysical uncertainties are large. The physics of star formation, feedback, dust production, and gas flow is notoriously hard to simulate. Many of the parameters used in models are calibrated using nearby galaxies, not primordial ones. So discovering that early galaxies were more efficient than expected is surprising, but not shocking. It fits within the messy, uncertain realm of galaxy formation, rather than the foundational pillars of cosmology. At the same time, the fact that some of these objects remain robust even after a year of scrutiny means they aren't mirages. They are real galaxies from the universe's earliest window, and they challenge parts of the model that didn't anticipate this level of early activity. This is what makes the discoveries exciting. They require refinement, not revolution. After 2 years of follow-up observations and increasingly careful modeling, the situation looks something like this. 1. Many early supermassive objects were overestimated. 2. A smaller but substantial group remains genuinely unexpected. 3. Spectroscopy has validated that many are truly ancient. 4. Some show structural maturity that standard timelines struggle to explain. 5. Their existence doesn't threaten cosmology, but it does stretch the physics of early galaxy formation toward more rapid growth. So while the story is less dramatic than the initial headlines suggested, it's actually more interesting scientifically, because when a result is too extreme, astronomers dismiss it as noise or misinterpretation. But when it's just plausibly beyond expectation, that's where real discovery begins. That's where new physics, or new astrophysics, tends to hide. These galaxies sit exactly in that zone, uncomfortable enough to demand explanation, but not so wild that they must be errors. That's what makes them so compelling. Nobody today doubts that Webb has uncovered galaxies in the first few 100 million years that are brighter, more structured, and possibly more massive than predicted. The debate is about interpretation. Are these galaxies unusually efficient outliers? Do they represent a population of rapid builders the early universe favored? Are simulations missing early processes that accelerate cooling or star formation? Did the first stars enrich their surroundings faster than expected? Is the initial mass function different in primordial environments? Each possibility points to a different flavor of early physics. None overturns the Big Bang. None undermines dark energy or dark matter. But several of them require reworking the recipe for how galaxies start their lives. That's why astronomers keep returning to these early giants. They're not errors, they're not illusions. They're the universe telling us that our picture of its first chapter is incomplete. And the gaps in that picture are exactly where new discoveries tend to emerge. When astronomers say these early galaxies shouldn't exist, they're not being dramatic. They're pointing out a specific conflict between what Webb is showing us and what the fundamental physics behind modern cosmology predicts. None of this comes from a place of wanting the universe to behave a certain way. It comes from equations that describe how matter collapses, how quickly gas cools, how long stars take to form, and how structures assemble under the influence of gravity. Those equations work beautifully for most of cosmic history. They explain the formation of galaxies like the Milky Way, the distribution of dark matter, the pattern of large-scale structure, and the ages of most stars we see. They line up with cosmic microwave background measurements, with the observed expansion of the universe, and with simulations that recreate galaxy evolution across billions of years. So when Webb reveals galaxies that seem to violate those expectations, the tension feels real, not hypothetical. The math says certain things shouldn't happen by a given time, yet they appear to have happened anyway. The core issue comes down to timescales. Structure in the universe forms gradually. Tiny fluctuations in the early plasma grew over hundreds of millions of years as dark matter pulled itself into clumps. Gas then fell into those clumps, cooled and formed the first stars. Those stars produced heavy elements, which were needed for later generations of stars and planets. All of this takes time, not because the universe is slow, but because the physics of collapse and cooling sets minimum rates. You can only form stars as fast as gas can condense. You can only enrich galaxies with heavy elements as fast as stars can produce and distribute them. You can only build massive galaxies at a certain pace because you're limited by the amount of matter that can fall into a halo and the rate at which that halo can grow. These limits aren't arbitrary. They come from well-tested physical models that correctly reproduce nearly everything else we observe. But Webb shows galaxies that appear to have raced far ahead of schedule. Some of the earliest massive candidates look like they've already converted enormous amounts of gas into stars within the first few 100 million years. To appreciate why this is so problematic, consider how long star formation takes even in a dense, turbulent cloud. Gas doesn't just collapse instantly, it's slowed by pressure, turbulence, radiation from nearby stars, and magnetic fields. It also needs to cool enough to lose energy and continue collapsing, and cooling itself depends on having molecules or heavier elements present. In the earliest moments of cosmic history, gas was nearly all hydrogen and helium. Without heavier elements to help radiate away heat, cooling becomes inefficient. When cooling is inefficient, star formation slows dramatically. You end up with small numbers of massive stars instead of rich, fast-growing clusters. That's why the first generation of stars, population 3 stars, was expected to be rare, large, short-lived, and not part of massive, well-organized galaxies. The idea was that these early giants would briefly illuminate the universe, seed it with the first heavy elements when they exploded, and then later, generations of stars could form more efficiently. But Webb is showing galaxies that already appear enriched with oxygen and other elements, meaning multiple cycles of star formation must have occurred before we see them. For that to be true, some of these galaxies would have needed to form their first stars almost immediately after cosmic expansion allowed neutral atoms to exist, within tens of millions of years, a blink on cosmic scales, and not just form them, but cycle through stellar lifetimes, supernova explosions, dispersal of metals, and cooling of enriched gas to form another generation of stars. Compressing this entire chain of events into such a short time frame stretches the limits of what the standard model predicts. Mass is another major issue. The size of a galaxy depends on the size of the dark matter halo that surrounds it. Dark matter halos grow through gravitational collapse and by merging with other halos. But this process has a maximum rate. You can't assemble a Milky Way mass halo instantly. Even in simulations where initial conditions are turned up to allow faster growth, halos need hundreds of millions of years to reach the scale implied by Webb's brightest early objects. When astronomers estimate the mass of these galaxies based on their brightness and spectra, the values sometimes come back so large that they would require dark matter halos, far more massive than what should exist by those early times. It's like discovering a city the size of Tokyo built during the Stone Age. It doesn't matter how impressive human ingenuity is, the required infrastructure simply shouldn't exist yet. Brightness creates another layer of tension. Many of the early Webb galaxies shine far more brightly than expected for their age. Under normal circumstances, brightness correlates with the number of young, hot stars. For a galaxy to reach that level of luminosity so early, it would need to form stars at an incredibly rapid rate, far faster than simulations predict. Star formation is self-regulating. When too many stars form too quickly, their radiation and supernova explosions push gas outward, slowing further growth. If early galaxies really formed stars at the extreme rates implied by their brightness, they would have blown themselves apart. Yet Webb's data suggests they somehow managed to grow without disrupting their supply of gas. Then there's the question of structure. The early universe should have been chaotic. Gas was flowing into halos from all directions. Mergers were frequent. Collisions between small proto-galaxies should have produced turbulent, irregular shapes. Instead, Webb reveals some galaxies with smooth, compact structures that imply stable rotation or centralized star formation. Even more surprising is the early presence of disk-like features, shapes that require calm, sustained growth rather than violent merging. This doesn't fit the traditional picture of early galaxy formation, where disks appear much later once the pace of mergers slows and gas settles into more stable configurations. Particularly striking is the reported discovery of a well-structured spiral galaxy existing only 1.5 billion years after the Big Bang. Spiral structure requires organized rotation, density waves, and a relatively undisturbed disk. That kind of order typically emerges after many billions of years of gradual evolution. Seeing it so early suggests that some galaxies rapidly achieve stability, contradicting assumptions that early galaxies were constantly stirred by frequent collisions. If spirals formed earlier than expected, it means either that matter settled into rotating disks unusually quickly, or that some regions of the early universe evolved differently than our broad models predict. Another part of the puzzle involves chemical enrichment. For a galaxy to show strong oxygen signatures only a few hundred million years after the Big Bang, it must have formed massive stars that lived, died, and exploded as supernovae in rapid succession. This shouldn't be impossible, but it should be rare and slow. Yet Webb is finding multiple galaxies with signs of significant metal enrichment. That means these galaxies weren't just experiencing their first burst of star formation, they were already in later stages of chemical evolution. Oxygen doesn't come from the Big Bang, it has to be forged inside stars. So oxygen at high redshift indicates a previous generation of stars had already lived out their brief lives. The timescale for this cycle is tight. Massive stars live only a few million years, but you still need several generations to enrich a galaxy substantially. Compressing that entire chemical journey into such an early window forces a rethink of star formation efficiency and the initial mass distribution of early stars. All of this feeds into a deeper problem: the amount of matter available. The universe has a finite supply of baryons, regular matter, and only a fraction of those baryons end up in galaxies. Most remain in diffuse forms for long periods. To build early massive galaxies, you'd need to collect an unusually high fraction of baryonic matter into compact structures. That contradicts models based on the cosmic microwave background, which show that matter should be fairly evenly distributed at early times with only slight variations. Those slight variations grow into galaxies later, but not fast enough to match the largest early objects Webb detects. Either the early density variations were larger than we thought, meaning structure formation began faster, or star formation was far more efficient at gathering gas, or some feedback mechanisms weren't as limiting as models assumed. Simulations add another layer of tension. When researchers run computer models of the early universe under standard cosmological assumptions, they almost never produce galaxies as massive or bright as those Webb is observing at the same epochs. When they try to adjust parameters, such as boosting star formation rate, accelerating halo growth, or reducing feedback, they can sometimes match one property of early galaxies, but not all of them at once. A scenario that produces enough mass often fails to produce enough brightness. A scenario that produces enough brightness usually overheats the gas and disrupts growth. Balancing these factors is difficult. The early universe isn't supposed to be capable of sustaining high-efficiency star formation and rapid mass assembly simultaneously. Yet Webb's observations imply that somehow, at least in some cases, it did. This raises uncomfortable questions about the timing of cosmic reionization. During the first few 100 million years, the universe was filled with neutral hydrogen that absorbed ultraviolet light. As stars and galaxies grew, they emitted enough radiation to ionize this gas and make the universe transparent to high-energy photons. This transition, called cosmic reionization, depended on how many early galaxies existed and how bright they were. If Webb's early galaxies are truly as abundant and luminous as they seem, they could have contributed far more to reionization than expected. That would imply not only that galaxies formed earlier than predicted, but that they played a major role in transforming the universe at earlier times as well. Reionization timelines are built from both observations and models, and these new discoveries force adjustments to both. The unusual objects Webb detects also complicate our understanding of dark matter. Dark matter forms the scaffolding for galaxies. Its distribution sets the pace at which structures emerge. If early galaxies are more massive and more abundant than expected, that might mean dark matter clumped together faster than models predict. But that would require amending assumptions built into the standard cosmological model, which itself is backed by extremely precise measurements of the cosmic microwave background. A faster collapse of dark matter halos might conflict with those earlier constraints. On the other hand, perhaps dark matter behaves differently at small scales than assumed. Some theories propose that warm or self-interacting dark matter could change the formation timelines, but these models typically slow down early structure formation rather than speed it up. Reconciling Webb's findings with dark matter physics remains a challenge. Another tension arises from feedback processes. In modern galaxies, intense star formation triggers winds, radiation pressure, and supernova explosions that blow gas out of galaxies, slowing further star formation. Early galaxies should have been even more vulnerable to feedback because they were smaller and had weaker gravitational wells. Yet, some of the early galaxies Webb sees seem to have formed stars extremely efficiently without being torn apart by their own stellar output. That suggests feedback may operate differently under early universe conditions, or that early gas supplies were so abundant and dense that they could withstand intense bursts of star formation. Both possibilities require revising long-standing models. Then there's the matter of how organized some early galaxies appear. Structure formation is expected to be hierarchical. Small objects form first, merge into larger ones, and eventually produce the stable disks and bulges seen in modern galaxies. This process is chaotic, producing irregular shapes and clumpy star formation. But Webb shows some early galaxies that look surprisingly smooth or compact. A compact structure implies the gas settled into a stable configuration quickly, leaving little evidence of violent mergers. That's surprising because early cosmic epochs should have been dominated by high merger rates. If early galaxies achieve stability faster than expected, that forces reconsideration of how turbulence, mergers, and gas inflow behaved in those early times. Some researchers have proposed that perhaps star formation in the early universe followed a different pattern. Maybe early gas clouds collapsed more directly because the universe was denser overall. Maybe the first massive stars formed in unusually large clusters, allowing chemical enrichment to proceed faster. Maybe black holes helped compress gas and trigger starbursts. But none of these ideas neatly solves the full puzzle. They each address one piece of the tension, but leave others hanging. The truth may involve a combination of multiple changes to existing assumptions. Not a single adjustment, but a reshaping of how we think early galaxies behaved. The reason all of this matters is that cosmology relies on consistency. If something doesn't add up at early times, the consequences ripple outward. The timeline for structure formation anchors other parts of the model: the growth of black holes, the birth of galaxy clusters, the emergence of the cosmic web. If galaxies formed earlier or faster than expected, that affects the interpretation of almost everything that follows. It doesn't necessarily mean the model is wrong, but it means the model is incomplete in ways that scientists are still working to understand. Webb isn't showing contradictions so severe that the entire cosmological framework collapses. Instead, it's showing that the earliest chapters of structure formation were more active, diverse, and efficient than the neat, gradual picture that had become standard. That's why scientists say these galaxies shouldn't exist, not because their existence is impossible, but because their properties sit outside the boundaries that theories predicted. And when observations push beyond those boundaries, models need refinement. It's happened many times before in astronomy. It's happening again now. The early universe is turning out to be more lively and more complicated than expected, and that's exactly the kind of surprise that drives progress. The moment astronomers realized that some early galaxies were far bigger, brighter, and more chemically mature than expected, attention immediately shifted to the engines inside them. If these galaxies really existed so early, something about the way stars formed in the young universe must have been operating differently from what most models assumed. Star formation is the heartbeat of galaxy growth. Change the pace of that heartbeat or the conditions that control it, and you can dramatically change how quickly a galaxy reaches maturity. What Webb is showing suggests that the earlier stars were not simply forming a bit faster. They may have been forming under a fundamentally different set of rules, producing effects that ripple outward through every aspect of a galaxy's life. This doesn't mean the basic physics of gravity, cooling, or thermodynamics were different then. It means the environment was so extreme, denser, hotter, less chemically enriched, and bathed in powerful radiation fields that familiar processes played out in unexpected ways. One idea receiving renewed attention is that the early universe might have been especially efficient at forming massive stars. Today, when gas clouds collapse, they tend to fragment into many smaller pockets, each forming a star a fraction of the Sun's mass. Bigger stars do form, but they're rare. This creates what astronomers call the initial mass function, a distribution that heavily favors low-mass stars. But that distribution assumes the presence of heavy elements and dust grains that help clouds cool and break apart. In the early universe, those ingredients were largely missing. Without metals to radiate away heat, gas clouds would stay warmer, resist fragmentation, and collapse into fewer, more massive stars. A population dominated by massive stars would shine incredibly brightly and produce intense radiation capable of transforming the environment around them. If early galaxies were filled with such stars, their overall brightness could rise rapidly, making them appear much more massive than they actually were. But even if their mass estimates are somewhat inflated, the underlying problem doesn't go away. Massive stars live fast and die young, releasing heavy elements into their surroundings within only a few million years. That means multiple generations of massive stars could appear in rapid succession, enriching galaxies with oxygen and other elements far earlier than expected. Still, even a top-heavy population of stars doesn't fully explain the growth rates inferred from the brightest early galaxies. To reach the stellar masses Webb is detecting, galaxies would need not only fast cycles of star formation, but also an abundant and steady supply of cold gas. The early universe certainly had plenty of gas, it was filled with it, but collecting that gas into a single galaxy-sized region requires substantial gravitational pull. That pull comes from the dark matter halo surrounding the galaxy. The surprising part isn't that gas was available, it's that some halos appear to have accumulated huge amounts of gas extremely quickly, leaving little time for the usual delays caused by turbulence, heating, or mergers. This suggests that early halos might have had unusually efficient gas accretion channels. Dense filaments of the cosmic web could have funneled gas directly into growing halos at high rates, creating continuous inflows that fed starburst after starburst. If these inflows remained stable and cold enough, galaxies could form stars at a pace that would be difficult to sustain at later times. Another angle concerns feedback, the star-driven winds, supernova explosions, and radiation that normally slow or halt star formation. In modern galaxies, feedback is what prevents star formation from spiraling out of control. When too many stars form at once, the resulting energy blows gas away, limiting further growth. But if early galaxies had deeper gravitational wells than expected, or if their gas densities were unusually high, they might have been able to hold onto their gas even while producing intense bursts of star formation. That would allow them to build mass rapidly without self-destructing. Another possibility is that early supernova feedback interacted differently with the surrounding environment. The intergalactic medium was denser and more uniform in the early universe, which might have trapped some of the energy from supernova, preventing them from sweeping gas out of galaxies as effectively as they do today. As a result, star formation could continue uninterrupted, creating a cascade of growth far faster than the calmer, regulated processes seen at later times. Chemical enrichment adds another layer to this picture. Metals help gas cool, and cooling is essential for star formation. That means the first stars may have kick-started a feedback loop of a different kind, one that accelerated rather than limited future growth. If a small number of extremely massive stars enriched their surroundings quickly, even a trace amount of metals could boost cooling rates dramatically. Once that process begins, star formation becomes easier, not harder. A galaxy could rapidly transition from a slow, metal-poor phase to a fast, metal-enhanced one. This might explain why Webb sees galaxies with surprisingly strong oxygen signatures so early. They may have crossed the threshold into efficient cooling far sooner than models predicted, enabling a rapid buildup of later generations of stars. There's also growing speculation that the chaotic nature of the early universe may have paradoxically created pockets of unusually calm conditions. Even though early cosmic epochs were filled with mergers and turbulence, some regions might have experienced brief periods where gas flows were steady and stable. In those zones, gas could collapse smoothly into rotating disks, allowing star formation to proceed at rates limited mainly by the sheer abundance of available material. The existence of early disk-like galaxies supports this idea. It suggests that structure didn't always have to form through violent collisions. Sometimes, the environment allowed smooth inflow and rotation to dominate. When gas settles into a disk, it can form stars in a more organized way, building galaxies that grow quickly without the disruptions typically expected in hierarchical models. Some researchers are also exploring whether early black holes played a role in accelerating galaxy growth. If seed black holes formed earlier or grew faster than expected, they could influence their host galaxies in multiple ways. Accreting black holes release enormous amounts of energy, sometimes triggering star formation in nearby gas clouds by compressing them. They might also help stabilize inflows of gas or create structures that channel material towards certain regions of the galaxy. This kind of black hole-driven influence is observed in later epochs, but its presence in the earliest eras remains uncertain. If Webb's early luminous objects include a mix of star formation and black hole activity, the combined effect could mimic starburst conditions on steroids, boosting brightness and reshaping the young galaxy's growth paths. The possibility of earlier than expected black holes raises another question. Could some of the most extreme early galaxies identified by Webb actually host growing black holes rather than just massive starbursts? Accreting black holes can produce light that looks similar to that of a bright young galaxy. Distinguishing between the two requires careful spectroscopy, and in many cases, the data isn't deep enough yet to separate them cleanly. If even a fraction of the earliest bright objects turn out to be powered by black holes, that could ease some of the tension with star formation models. But it wouldn't solve everything. Black holes themselves need time to form and grow, and the earliest epochs don't offer much of it. Rapid black hole growth also requires abundant cold gas, which leads back to the same question. How did these early systems gather such large supplies so quickly? Another possibility lies in how star formation was spatially distributed. Modern galaxies often form stars in localized regions, with large sections sitting relatively quiet. Early galaxies may have had more uniformly dense conditions, allowing star formation to occur across much of their volume at once. Instead of a handful of dense clouds collapsing into stars, enormous swathes of gas could have been forming stars simultaneously. This kind of widespread starburst could produce the brightness Webb observes without requiring exotic physics. But such uniform star formation demands extremely stable gas inflows and minimal disruption from feedback, which circles back to the idea that some early environments were unusually conducive to rapid growth. The biggest shift prompted by Webb's early discoveries may be conceptual rather than specific. For years, models treated early galaxy evolution as a more sluggish, limited version of what happens later. The assumption was that early galaxies had to work harder to form stars because they lacked the heavy elements that make cooling efficient. But perhaps that assumption flips the story. In a denser universe with gas packed more tightly and gravitational collapse happening more rapidly, galaxies might have had more energy at their disposal. Instead of being limited by low metallicity, early star formation could have thrived because the raw conditions favored rapid collapse even without metals. Only after the universe expanded and cooled did the pace of star formation become more moderate and self-regulated. In other words, the early universe might not have been trying to catch up to later epochs. It might have been racing ahead in ways that only now are becoming clear. This shift also affects our understanding of galaxy sizes. Some of the early galaxies Webb sees are surprisingly compact, packing huge numbers of stars into very small volumes. Compactness increases gravitational pull and makes it easier for galaxies to hold onto gas despite supernova feedback. A compact galaxy can build mass faster because its deeper potential well exerts a stronger grip on inflowing material. This might help explain how early galaxies maintained such intense star formation rates. As gas reached the central regions, it stayed there, primed to form stars efficiently. In these conditions, even a small change in density or cooling rate could produce dramatic results. A compact galaxy with a top-heavy initial mass function, strong inflows, and limited feedback loss could grow at a pace that appears impossible under calmer, modern conditions. The implications of this extend beyond the early universe. If early galaxies formed stars differently, that changes the baseline assumptions used in simulations of galaxy evolution. Many of the relationships observed in later galaxies between mass, size, metallicity, and star formation rate may not apply at the earliest times. If the rules were different then, models need to account for that difference, rather than forcing early galaxies into patterns derived from mature systems billions of years old. Webb is already challenging simple extrapolations that treat early galaxies as scaled-down versions of modern ones. The data suggests that the earliest galaxies were not embryonic versions of today's giants. They were intense, fast-growing structures that operated under extreme conditions rarely found again afterward. Another consequence concerns cosmic reionization. If early galaxies were more numerous, more luminous, or more efficient at forming stars than expected, they could have produced far more ultraviolet radiation than models predicted. That radiation would help strip electrons from neutral hydrogen, making the early universe transparent. For years, scientists debated how the universe reionized so quickly. Webb's early galaxy counts suggest that star formation in the first few 100 million years was vigorous enough to supply much of the necessary energy. This doesn't solve every detail of reionization, but it provides a plausible path toward reaching the required photon budget without invoking exotic sources. Galaxies with rapid early growth also influence how large-scale structure unfolded. If more mass collected in early galaxies, some regions of the universe might have evolved faster than others, leading to uneven development of the cosmic web. Later structures, galaxy clusters, filaments, voids, could have inherited those early imbalances, meaning that the distribution of matter today might reflect surprisingly rapid early processes. Webb's discoveries open the door to considering that variability, forcing simulations to incorporate more diversity into the early stages of structure formation. All these implications emphasize a single point. Star formation and galaxy growth in the early universe were not simply sped-up versions of the processes we observe now. They were shaped by a unique environment, denser, hotter, chemically simpler, but rich in gas and driven by rapid gravitational collapse. The surprise is not that early galaxies formed, but that they formed so efficiently, with such remarkable outcomes so early. Webb has shown that galaxies wasted no time building themselves into complex systems, and the mechanisms that enabled that growth defy many assumptions that guided decades of research. As astronomers dig deeper into Webb's data, the picture that emerges is one of a universe eager to build, with the earliest stars and galaxies forming not reluctantly, but aggressively. Instead of gradual, hesitant beginnings, the cosmos seems to have launched into a phase of rapid assembly and intense star formation almost as soon as physical conditions allowed it. And while this doesn't rewrite the laws of physics, it does require rethinking how those laws played out under the extreme conditions of the young universe. The earliest galaxies weren't limited by the same bottlenecks we see today. They operated under a regime primed for speed, and Webb has finally given us a clear look at just how fast that growth could be. For decades, the standard cosmological model, lambda CDM, has served as the backbone of our understanding of the universe's evolution. It explains the distribution of galaxies, the formation of large-scale structures, the cosmic microwave background, the abundance of elements, and the accelerating expansion of the universe. It has survived intense scrutiny, precision measurements, and the rise of new observational technologies. But every model has its stress points, and Webb has revealed some that strike deeper than many astronomers expected. The question isn't whether lambda CDM is wrong. The question is whether the assumptions layered on top of it about how galaxies should form under its umbrella were too conservative, too simplified, or too tied to the ways galaxies behave in the modern universe. Still, there's an unavoidable tension forming. If galaxies in the first few 100 million years were far bigger, brighter, or more structured than predicted, does the foundational framework that describes the universe's growth from the Big Bang to now truly capture what was happening in those earliest moments? To be clear, lambda CDM does not itself specify the details of how galaxies form. It sets the stage, a universe dominated by cold, dark matter, with dark energy driving cosmic acceleration, ordinary matter comprising a small fraction, and gravitational instability causing small fluctuations in density to grow into the cosmic web. Within that framework, galaxies emerge inside the densest knots of dark matter. But the model doesn't tell us how efficiently stars form inside those halos, how turbulence behaves, how gas cools, or how feedback from stars or black holes regulates growth. Those are layered assumptions, derived from later epochs where astronomers can directly observe the details of gas physics. The tension arises because many of the earliest galaxies that Webb sees appear to sit outside the range predicted by simulations that use these assumptions. The dark matter halos in lambda CDM can, in principle, form early enough to host these galaxies. No law forbids that. But the speed and scale at which baryonic matter, real gas and real stars, condensed into those halos seem to stretch the expected timelines to the breaking point. One of the sharpest points of friction involves the expected mass distribution of early halos. In lambda CDM, dark matter begins clumping almost immediately after the Big Bang, but the formation of massive halos large enough to host today's big galaxies takes time. Most simulations predict that galaxies with masses similar to the Milky Way shouldn't appear until several billion years after the Big Bang. Before that, the universe should be populated by much smaller proto-galaxies, still in the process of merging and growing. Webb's observations of galaxies that appear not just moderately large but truly massive at only a few 100 million years old suggest that either those halos formed faster than simulations expect, or the baryons inside them formed stars far more efficiently than assumed. If halos this large existed that early, it could imply that dark matter clumped more effectively at small scales than expected. That would put pressure on the coldness assumption in lambda CDM, how slowly dark matter particles move and how tightly they can bind together. If dark matter were slightly colder than modelled, it might form small-scale structures more quickly, giving early halos a head start. Conversely, if dark matter behaved in more complex ways, self-interacting, decaying, or possessing slight thermal motions, the early halo distribution could shift. Some theorists have seized on the Webb results to revisit these possibilities. Then there's the issue of star formation efficiency. Galaxies do not convert all their gas into stars. In fact, most modern galaxies are surprisingly inefficient at it, forming stars at a fraction of the rate that the raw availability of gas would permit. Feedback processes, supernova winds, radiation pressure, turbulence slow things down. In lambda CDM-based simulations, these feedback processes are essential for matching observed galaxies at later times. If galaxies formed stars with perfect efficiency, the universe today would look dramatically different. But early galaxies may not have conformed to the rules inferred from later epochs. If they were forming stars close to the maximum possible rate, it would dramatically accelerate their growth, allowing them to reach high masses while still remaining consistent with lambda CDM's halo formation timelines. In this scenario, the tension lies not with the cosmology but with our understanding of baryonic processes. The challenge is that simulations that adopt such high early efficiencies often break when extended forward in time. They produce galaxies that are too massive, too bright, or too compact at later epochs. Reconciling extreme early growth with normal later behavior requires some mechanism to sharply reduce efficiency after the first few 100 million years, a detail that no model currently incorporates cleanly. Another cosmological sticking point involves the timeline of cosmic structure formation. If galaxies were already well developed at extremely high redshifts, it implies that density fluctuations must have grown faster than expected. These fluctuations, the tiny variations imprinted on the cosmic microwave background, are the seeds from which all structure grows. Lambda CDM predicts how they should evolve, and observations of the cosmic microwave background and large-scale structure broadly support those predictions. But if the early universe produced massive galaxies more quickly than expected, it raises the question of whether some regions experienced enhanced growth. Were density fluctuations slightly larger in certain patches? Did the early universe contain matter distributions slightly outside the statistical expectations? While small deviations are permissible, large or widespread ones could threaten the internal consistency of the model. Some theories propose that early growth might cluster along the densest nodes of the cosmic web, where conditions were unusually favorable for rapid collapse. If Webb is preferentially detecting those extreme regions, the apparent tension with Lambda CDM could be partly an observational bias. Webb sees the brightest objects most easily, and those objects may sit in the most over-dense environments. But even that explanation requires those environments to be much more evolved, much earlier than standard models predict. The existence of well-structured early disks and potential spiral features adds another layer of complexity. Lambda CDM predicts that mergers should be frequent early on. Those mergers tend to disrupt disks, producing irregular, clumpy structures rather than ordered rotation. Yet Webb has revealed several systems whose light profiles indicate organized motion, suggesting that rotating disks formed far earlier than hierarchical models expected. The presence of a grand design spiral only about 1.5 billion years after the Big Bang is especially striking. Spiral structure requires time, stability, and repeated cycles of star formation and feedback, all hard to achieve in the highly merger-driven landscape assumed for the early universe. One way to reconcile this is to argue that mergers were less common in certain regions, or that gas inflow from the cosmic web played a more stabilizing role than assumed. Another explanation is that early halos were smoother and more quickly assembled, providing more stable environments for disks to form. But these explanations require adjustments to the understanding of when and how hierarchical growth occurred, nudging Lambda CDM's predictions toward earlier structure formation without fully breaking the model. A deeper cosmological challenge emerges when considering the timeline of rionization. If early galaxies were far more numerous or luminous than expected, they could have contributed more photons to the ionizing background, potentially reionizing the universe earlier or faster. While this doesn't contradict Lambda CDM, it does shift expectations for the thermal state of the early intergalactic medium. It could imply that the process of reionization was more gradual, more patchy, or more dominated by faint galaxies than earlier models suggested. A faster or more photon-rich reionization could influence the formation of later structures by altering gas temperatures and the distribution of ionized regions. This may not break Lambda CDM, but it complicates the picture of how galaxies and the intergalactic medium influenced each other. Some theorists have proposed more radical explanations. Perhaps the early universe underwent brief phases of enhanced expansion or contraction. Perhaps dark energy behaved differently in the first billion years. Maybe early dark matter possessed self-interactions that altered small-scale structure formation. These ideas range from conservative adjustments to exotic departures. The trouble with these explanations is that they tend to affect other observables: galaxy clustering, the cosmic microwave background, gravitational lensing, and must be carefully constructed to avoid breaking the many successes of Lambda CDM. The standard model has passed an extraordinary number of tests, so any alteration must preserve its predictive power across many scales. That's a high bar. A more grounded interpretation suggests that while Lambda CDM remains robust, simulations must incorporate more extreme early baryonic physics. The model may not need rewriting, just recalibration. This view argues that early star formation was indeed faster, feedback was less effective, gas inflows were more stable, and cooling processes were more efficient than previously thought. If so, the dark matter scaffolding predicted by Lambda, CDM, could support the rapid galaxy growth Webb sees. The model stands, but the details of galaxy formation, especially at high redshift, require major updates. In this interpretation, the problem lies not with cosmology, but with the tendency of simulations to extend modern galaxy behavior backward in time. The universe was more chaotic, more energetic, and more conducive to rapid assembly than most models accounted for. But even this measured interpretation acknowledges that the tension is real. Webb's discoveries didn't break cosmology, but they exposed blind spots in how cosmology has been applied. Lambda CDM can accommodate early massive halos. It predicts them at some statistical level. What strained the models was the assumption that baryons inside those halos would form stars slowly and inefficiently. That assumption may now be dead. The early universe was not the quiet, tentative environment many imagined. It was a place where gravity, gas dynamics, and cooling worked together at a pace modern galaxies cannot match. The philosophical impact of this shift is significant. For years, astronomers assumed that the early universe was a simpler version of today's cosmos: fewer metals, smaller galaxies, slower growth. Webb has revealed a universe that was not simple, but fierce. Not hesitant, but ambitious. Not slowly assembling, but racing through its early phases. If Lambda CDM remains the correct framework, then its earliest chapters were written with an intensity models did not anticipate. This leads to a broader reflection on the limits of prediction. Cosmology excels at describing large-scale trends, but the details of galaxy formation depend on complex, non-linear physics that resist simple modeling. Webb has shown that nature may have exploited those complexities to reach outcomes far more diverse and unexpected than the smooth lines drawn in simulations. The early universe was a place where gravity and gas engaged in a high-speed dance, guided by laws we understand but enacted under conditions we've only now begun to see. For Lambda CDM, the message is not one of failure but of opportunity. Every tension Webb reveals pushes theorists to explore the boundaries of the model, refine its assumptions, and confront the full complexity of the early cosmos. If the standard model survives this stress test, and most indicators suggest it will emerge stronger, more nuanced, and better equipped to describe the universe's first billion years. If it does not, it will be because Webb has illuminated paths that require new physics, new ingredients, or new ideas. Either outcome deepens our understanding. What's clear is that cosmology now stands in a moment of productive uncertainty. Webb has shown that galaxies were not content to wait politely for billions of years to grow. They leapt ahead, forming stars, structure, and complexity with astonishing speed. Whether that speed pushes cosmology into a new phase or simply forces a harder look at the physics of early star formation remains the question of the moment. What is certain is that a universe that once seemed predictable has become thrillingly complicated again, and in that complication lies the next era of discovery. When astronomers confront results that stretch the boundaries of what models predict, the first instinct isn't to tear down the existing theory. It's to try to understand whether something else, something less radical, could be happening. Webb's early discoveries pushed researchers into that exact mode of thinking. Before rewriting cosmology, it makes sense to ask whether the observations could be interpreted in a different way, or whether the objects being examined aren't quite what they appear to be. And this is where a whole range of alternative explanations begin to surface. Not excuses for the data, but serious possibilities that need to be weighed carefully, because the earliest universe is a tricky environment to observe, and the objects within it can be deceptive. One of the first alternative explanations involves the idea that some of these unusually bright objects may not be galaxies in the conventional sense. They could be dominated by energetic processes centered on black holes rather than starlight. When a supermassive black hole accretes material, the gas near it heats to extreme temperatures and emits intense radiation. This can make the surrounding region incredibly bright, sometimes outshining the entire galaxy that hosts it. At great distances, especially the kind Webb is probing, that bright core can mimic the appearance of a massive galaxy, even if the underlying stellar mass is far smaller. If some of the early massive candidates are actually powered by early black holes that grew faster than expected, then the tension with galaxy formation models relaxes. But that explanation carries its own interesting implications, namely that black holes might have been forming and growing at astonishing rates in the early universe. That possibility opens a different line of questions because early black hole growth is itself an unsolved puzzle. Another alternative is that some of the objects Webb detects may be gravitationally lensed. Lensing occurs when a massive object between us and a distant galaxy bends and magnifies the light from that faraway source. In many cases, lensing boosts brightness by factors of 2, 3, or even 10, making galaxies appear more luminous and larger than they truly are. If even a small fraction of Webb's early massive galaxies are actually lower mass galaxies artificially brightened by lensing, the discrepancy between observation and theory weakens. But lensing leaves signatures, distortions, arcs, stretched shapes, and those aren't always obvious in the earliest Webb images. Some lensing configurations produce subtle effects that require extremely detailed modeling to confirm. That means it's entirely possible that a number of bright early objects have hidden lensing contributions that haven't been recognized yet. Even mild magnification can shift an object from exotic and impossible to unexpected but plausible. A related possibility is that selection biases within Webb's surveys may be leading astronomers to notice the brightest, most extreme galaxies first. When you survey the early universe, faint galaxies are much harder to detect than bright ones. Even a telescope as powerful as Webb can only reveal objects above a certain threshold of brightness and clarity. That means the first galaxies we see are likely the outliers, the most luminous, most rapidly forming, or most compact systems. If the early universe contained a population of extreme galaxies that were only a tiny fraction of the total, they could dominate the observable sample long before telescopes reveal the more typical, less dramatic population. This bias doesn't negate the existence of early massive galaxies, but it reframes their significance. Instead of representing the norm, they may represent the far tail of the distribution, the cosmic overachievers. And if that's the case, the cosmological tension becomes a question of statistics and detection limits rather than a fundamental break in theory. Another line of thought suggests that some of the objects might not be fully formed galaxies at all, but rather dense, starburst regions undergoing incredibly rapid episodes of star formation. Starburst regions can outshine normal galaxies because they produce enormous numbers of young, hot stars in a very concentrated space. In the early universe, such bursts might have been more common, driven by the high availability of cold gas, frequent collapses, or intense environmental pressures. If these bursts dominate the light Webb sees, the underlying stellar mass could be lower than initially inferred. The galaxy may appear enormous and evolved when its true mass is more modest. To evaluate this explanation, astronomers need detailed spectra, not just broadband imaging. Spectra reveal the ages of stars, the chemical signatures, and the presence of hot accretion disks, or ionized gas. Without that high-resolution information, it's easy to misjudge the true nature of a bright object. Webb has also shown that the early universe may have produced stars under different conditions than the present. Some researchers propose that early star formation favored heavier, more luminous stars, a top-heavy initial mass function. If stars formed with a greater proportion of massive members, the total brightness of a galaxy could be wildly inflated compared to the actual amount of mass inside it. Massive stars burn hotter and produce far more light per unit mass than the smaller, more common stars that dominate galaxies today. If early galaxies had top-heavy stellar populations, they would appear far more massive and luminous from a distance, even if they hadn't formed much more material than predicted. This explanation fits neatly with another idea, that early cooling mechanisms, driven by primordial gas and rapid collapse, allowed star-forming clouds to reach conditions favorable for forming large numbers of massive stars. A top-heavy population would also enrich galaxies more quickly, producing elements like oxygen or carbon at higher rates. That could help explain the chemically mature galaxies Webb sees at extremely early times. Chemical maturity itself opens another lane for alternative explanations. Perhaps the observed chemical signatures arise from processes other than normal star formation. One proposal involves early, massive black holes enriching their surroundings through energetic outflows or radiation-driven winds. If black holes formed extraordinarily early, their environments could produce ionized gas and certain emission features that mimic metal-rich regions without requiring several generations of stars. This would be a surprising shift in understanding, replacing a star-dominated early universe with one where black holes played a more active chemical role than previously thought. Another possibility is that early galaxies accumulated gas in more organized and efficient ways than models assume. If inflows from the cosmic web fed them directly with cold gas, bypassing the heating processes expected in later epochs, then star formation could proceed at nearly maximal rates. These streams could also stabilize rotating disks earlier than expected, allowing the formation of orderly structures even in an era dominated by mergers. This explanation still fits within the standard cosmological framework, but it requires a shift in assumptions about how quickly gas can flow, cool, and settle. Hydrodynamic simulations often struggle with the precise physics of cold streams at high redshift, so it's possible the universe simply took advantage of mechanisms models treat too conservatively. One of the more unconventional explanations suggests that some high redshift objects might not be galaxies at all, but something more exotic, clusters of primordial objects formed through processes not dominant today. These could include dense clusters of extremely massive stars, remnants of early star-forming events, or even hypothetical objects such as dark matter-powered stars. While these ideas sound speculative, they arise because the conditions of the early universe were fundamentally different from today. Densities were higher, temperatures varied rapidly, and the distribution of dark matter may have allowed unusual structures to form briefly before transitioning into more standard configurations. If even a small number of these unusual objects survived long enough to be observed by Webb, they could mimic early galaxies without requiring the same formation timescales. Another explanation involves the complexities of redshift measurement. Determining distances to very faint galaxies is delicate work. Photometric redshifts, which rely on broadband color measurements, can sometimes produce ambiguous results. A galaxy might appear to sit at extreme distances when, in reality, it's much closer but dustier, or dominated by unusual types of stars, or affected by intervening absorption. Spectroscopic confirmation is the gold standard, but many of the earliest Webb discoveries still await it. If even a subset of the most extreme candidates turn out to be lower redshift contaminants, the frequency of impossible galaxies drops. This doesn't explain away the confirmed high redshift giants, but it could thin out the upper end of the distribution and soften the tension. And there's also growing interest in the idea that early dust may have played a bigger role than expected. Dust absorbs certain wavelengths and re-emits others, which can skew interpretations of brightness, mass, and age. If early dust formation was more efficient, perhaps due to early supernovae producing large amounts of grains, then the spectral energy distributions of early galaxies might appear older or more massive than they are. Dust can also obscure young stars while emphasizing older ones, misleading mass estimates. If so, the universe may not be full of overgrown giants, but rather dusty, rapidly forming galaxies whose true characteristics only emerge with detailed modeling. Some theorists propose hybrid explanations, suggesting that several of these effects could combine. A galaxy might be mildly lensed, undergoing a starburst, composed largely of massive stars and affected by early dust, all at once. Each effect might be subtle, but together they could significantly alter the inferred mass or age. This kind of multi-component explanation fits the idea that early galaxies were far more diverse than modern analogues. The early universe wasn't uniform, it was a landscape of rapidly shifting conditions where extreme environments and unusual combinations of factors were likely common. A more cautious alternative centers on the limitations of simulations. Models often rely on approximations and simplified physics to remain computationally tractable. They assume certain feedback efficiencies, star formation thresholds, collapse mechanisms, and turbulent behaviors based on observations from later epochs. But the early universe may not have followed those rules. If simulations underestimated the speed, intensity, or chaotic nature of early star formation, the mismatch with Webb's observations originates not from flawed cosmology, but from the assumptions built into the computational tools used to predict galaxy behavior. This explanation doesn't dismiss the observational surprises, it reframes them as a reminder that models are only as good as their assumptions. The final alternative is simply that the universe was more variable in its earliest billion years than anticipated. Instead of a smooth statistical progression from small to large galaxies, early growth may have been punctuated, patchy, and dominated by rare but extremely rapid events. In that picture, Webb is seeing snapshots of those rare early accelerators, regions where conditions lined up perfectly for runaway growth. These regions don't break the overall cosmological model. They just represent the upper limits of what's possible within it. If so, the tension with theory is not a sign of failure, but proof that nature explored its full range of options. Now, each of these alternatives carries different implications for how we interpret Webb's findings. Some challenge assumptions about early black holes, some reframe star formation physics, some highlight observational biases, and some force revisions to simulation strategies. None dismiss the significance of the discoveries. They simply remind us that the universe is more complicated than any single explanation can capture. The truth may involve several of these ideas working together, and as more data arrives, astronomers will be able to test these possibilities with greater precision, narrowing down which ones truly describe the earliest structures in the cosmos. Astronomers now find themselves in a moment where almost every new Webb discovery raises fresh questions, and the only way to move from speculation to clarity is through deeper, more targeted observations. The surprises uncovered so far have mostly come from broad surveys, snapshots of large regions of sky designed to reveal thousands of faint, distant dots. Those surveys are ideal for identifying candidates, spotting outliers, and mapping trends, but they aren't enough to untangle the detailed physics behind each object. For that, researchers need far more complete information than brightness or shape alone can provide. They need spectra, high-resolution follow-ups, multiple wavelength perspectives, and repeated observations over years. And because Webb has already revealed that the early universe is far more complex and dynamic than expected, the next phase of research depends on shifting from discovery mode to diagnosis mode. It's no longer about simply finding unusual galaxies. It's about figuring out exactly what they are and how they got that way. One of the clearest needs is widespread spectroscopic confirmation of the most extreme high redshift candidates. A galaxy's redshift isn't just a measure of its distance. It determines its age in cosmic time and shapes nearly every interpretation about its mass, temperature, chemical composition, and formation history. While Webb's imaging can strongly suggest a particular redshift, only a spectrum provides unambiguous confirmation. The challenge is that the faintest, most distant galaxies require long exposures, sometimes dozens of hours, to acquire clean spectral lines. That's a huge investment of telescope time, and the queue for Webb is already extremely competitive, but without those spectra, astronomers can't be sure whether a galaxy truly sits in the earliest few 100 million years, or whether some combination of dust, unusual stellar populations, or intervening absorption makes it merely look that distant. The need for spectra becomes even more critical when interpreting galaxies that appear chemically mature. When Webb detects oxygen, carbon, or other heavier elements in systems that should barely have had time for one generation of stars, it raises questions that only detailed line strengths, ratios, and emission profiles can answer. Spectra allow astronomers to distinguish between enrichment from normal stars, enrichment driven by early black holes, or signatures produced by extreme starbursts. They also reveal whether certain lines are broadened by rotation, turbulence, or outflows, offering clues to how chaotic or organized a galaxy might be. Without this level of detail, every interpretation, no matter how careful, carries large uncertainties. Another major need involves observing these galaxies at wavelengths beyond Webb's reach. Webb covers the infrared spectrum better than any previous space telescope, but some of the physical processes in early galaxies leave signatures at wavelengths best observed by other instruments. Radio observatories such as ALMA can study cold gas, dust content, and molecular structures that are invisible to Webb. These observations are essential for determining how much gas is available for star formation and how efficiently a galaxy is converting that gas into stars. If early galaxies contain huge reservoirs of cold gas, it could help explain their rapid growth. If instead they show signs of early depletion, it could suggest short, intense starburst phases followed by quiescence, far different from the slow, steady star formation seen in galaxies today. Likewise, future ground-based telescopes will play an important role. The upcoming generation of giant observatories, such as the Extremely Large Telescope and the 30-meter telescope, will have the sensitivity and resolution to perform spectroscopy on extraordinarily faint objects with a level of detail that complements Webb's strengths. Their adaptive optics systems will allow astronomers to resolve small structures, measure rotation curves, and determine whether early disks or spiral features truly exist in some of these distant systems. Even more importantly, these ground-based telescopes can conduct wide spectroscopic surveys, collecting data on larger samples of early galaxies than Webb alone could handle. Another type of follow-up that astronomers need involves temporal monitoring, revisiting the same objects months or years later to see if their brightness, structure, or spectral properties change. At first glance, that might sound unnecessary for galaxies so far away that their evolution should be imperceptible on human timescales. But some of the brightest early candidates may be quasars or early black hole-dominated systems, and these can vary noticeably even over short intervals. Monitoring variability helps distinguish between light from stars and light from active galactic nuclei, directly addressing one of the biggest uncertainties in interpreting Webb's early results. If a supposedly massive galaxy flickers or brightens unpredictably, it likely harbors a rapidly growing black hole rather than being a purely stellar system. Astronomers also need more precise measurements of the sizes of early galaxies. Even small errors in estimating size can dramatically affect interpretations of density, mass, and star formation intensity. If early galaxies are much more compact than today's, they could reach extreme mass densities, even with modest total mass. Webb's resolution is remarkable, but for the tiniest galaxies at the edge of detectability, the distinction between a compact starburst and a large, massive galaxy can be razor-thin. High-resolution imaging from multiple orientations, sometimes achieved through natural lensing by foreground clusters, can improve size estimates and help determine whether these early systems were truly gigantic or simply unusually concentrated. Lensing studies themselves are another critical resource. Webb has already captured deep views of galaxy clusters that act as natural magnifying glasses. These fields, known as lensing clusters, can reveal extremely faint galaxies that would otherwise be invisible. But to interpret the magnification correctly, astronomers need detailed lens models that map how the cluster's mass distorts space. Better models mean better mass and brightness estimates for the lensed galaxies. If magnification has been underestimated for some of the early giants, then their true masses may be lower. Conversely, if magnification was overestimated, the tension with galaxy formation models grows. Improving lens reconstructions is a painstaking process, requiring multi-wavelength observations of the clusters themselves and careful mapping of their dark matter distributions. Another area where future observations will help enormously is the measurement of stellar populations in early galaxies. Understanding the age distributions, temperature spreads, and metallicity variations within a system can reveal whether it grew steadily or through bursts. Webb can access some of this information already, but pushing deeper into the earliest epochs requires instruments that can observe fainter populations at higher spectral resolution. Identifying the contributions from older stars could clarify whether some early galaxies formed the bulk of their mass extremely early and then slowed down, or whether they are still in the throes of building themselves rapidly. The next generation of space telescopes will be crucial as well. Although Webb is transformative, it isn't the end of the story. Future missions are already being designed to probe the universe in ways Webb cannot. Some proposed instruments will map hydrogen emission across the early universe, tracing the process of reionization in fine detail. Others aim to observe the cosmic microwave background with greater precision, tightening the constraints on density fluctuations that seeded early galaxies. If the early universe was patchier or more rapidly evolving than expected, these missions will reveal the subtle fingerprints of that complexity. Another key need is deeper theoretical modeling. Observations alone won't solve the puzzle of early massive galaxies. Astronomers need simulations that explore a wider range of physical assumptions, pushing into regimes not typically modeled. That includes simulations with extreme star formation efficiencies, simulations that explore top-heavy initial mass functions, simulations that incorporate more realistic turbulence and gas dynamics, and simulations that allow for rapid early black hole growth. These models must also track how galaxies evolve afterward, ensuring that the aggressive early behavior doesn't contradict the observed properties of galaxies at later times. The best simulations today are highly sophisticated, but even they struggle with the full complexity of early cosmic conditions. As computing power increases and algorithms improve, simulations will be able to more faithfully reproduce the interplay of dark matter, gas, stars, and black holes at the highest redshifts. These improvements are essential for interpreting Webb's observations without jumping prematurely to conclusions about cosmology. There's also a growing realization that astronomers need better statistical frameworks to interpret early universe data. When dealing with the faintest, most distant objects, uncertainties are huge and often correlate with one another. Traditional methods of estimating mass, brightness, and redshift don't always capture the full landscape of possible interpretations. New statistical models that incorporate uncertainty more realistically will help avoid overstating the significance of any one observation. This matters because some of the current tension with galaxy formation models comes not from the raw data, but from the assumptions built into the interpretation pipeline. Another valuable tool will be the expansion of Webb's Deep Field program. The initial deep fields revealed a wealth of unexpected objects, but they cover extremely small patches of sky. Expanding these fields to larger areas will help astronomers determine whether the early giants are rare, extreme cases, or representative of the broader population. If they turn out to be rare, the implications for cosmology are milder. If they're common, the tension becomes unavoidable. Large, statistically robust surveys will clarify whether the early universe was dominated by rapid growth, or whether we've simply been fortunate or unfortunate enough to find a few extreme examples. Finally, there is the need for long-term continuity. Webb is designed for many years of operation, but its discoveries open questions that will continue far beyond its lifetime. Building a coherent picture of the early universe requires a collaborative sequence of observations across decades. Future instruments will have to follow up on what Webb starts, probing deeper, wider, and with different methods. It's similar to how the Hubble Space Telescope opened a window into galaxy evolution, and subsequent telescopes, Spitzer, ALMA, large ground-based observatories, filled in details Hubble couldn't see. Together, all these observations, instruments, and modeling efforts will gradually strip away uncertainties and reveal the true nature of the early giants Webb has uncovered. Whether they turn out to be products of unusual conditions, observational quirks, or genuinely paradigm-shifting structures, the next decade of astronomy will revolve around understanding them. Webb has given the universe a chance to surprise us again, and the only way to meet that challenge is with deeper data, sharper tools, and a willingness to revise even the most established ideas when new evidence demands it. As researchers digest the growing pile of puzzling results, the picture of the early universe is no longer the quiet, slowly evolving scene described in many textbooks. Webb's findings suggest something far more dynamic, an era in which matter organized itself faster than anyone expected, star formation operated under different rules, and galaxies didn't simply grow through the slow drip of hierarchical merging. Everything from the efficiency of gas collapse to the timing of chemical enrichment may need to be reconsidered, and the best way to understand how big this shift might be is to step back and trace how our mental model of early cosmic history is beginning to bend. The traditional view is relatively straightforward. After the Big Bang, the universe cooled, light elements formed, and a long period of darkness followed. Gravity gradually pulled tiny density fluctuations together, forming small halos of dark matter. Into these halos, hydrogen and helium gas fell, slowly forming the first stars. Those stars enriched the surrounding gas with heavier elements, which helped the next generation cool more efficiently, making star formation easier. Over hundreds of millions of years, small proto-galaxies merged, creating larger and more organized systems. It was a slow, bottom-up process. Big galaxies came late, spirals came even later, and chemical complexity took time because it depended on generations of stars recycling their material. But the galaxies that Webb is uncovering, some of them appearing massive, compact, chemically developed, and even orderly, are not behaving as though they had only a few 100 million years to work with. They look like the products of processes running at full throttle. They seem to have skipped steps, or at least compressed them into a much shorter timeline. Instead of long, steady growth, many of them look like they formed quickly, burned brightly, and assembled efficiently, as though something in the early universe unlocked a mode of construction we haven't fully modeled yet. One implication is that star formation may have been more efficient in early halos than anyone expected. Gas in the young universe was denser, hotter, and more uniform, which might have allowed it to collapse much faster once it entered a gravitational well. In that environment, the cooling channels that allow gas to shed energy and collapse might have operated more aggressively. It's possible that the first episodes of star formation erupted in powerful bursts, rapidly converting a large fraction of available material into stars in just a few million years. That would create bright, compact stellar populations that mimic the appearance of mature galaxies, even if they formed incredibly quickly. But to reach the masses Webb is detecting, these bursts would have to be pushed to extremes compared to anything seen in modern galaxies. If that's the case, then the early universe wasn't just building faster, it was building fundamentally differently. Another angle is that dark matter halos may have been more efficient at capturing and holding gas. In cosmological simulations, halos grow steadily as they pull in dark matter and gas from their surroundings. But if conditions right after the Big Bang made some halos grow faster than predicted, either through enhanced early density fluctuations or a faster rate of accretion, then galaxies inside those halos would have had more raw material to fuel their early construction. This wouldn't require new physics, but it would require a shift in how we think about the timing of structure formation. The early universe might have produced more massive halos earlier and more frequently than standard models currently allow. That would ripple through nearly every assumption about early cosmic evolution. The presence of early chemical complexity also pushes the picture toward a more active early cosmos. Metals, in the astronomical sense, represent the remains of earlier stars. Their presence in galaxies that existed merely 300 million years after the Big Bang implies that at least one full generation of stars must have formed, lived, and died extremely quickly. That suggests an initial mass function skewed toward massive stars, stars that burn through their fuel rapidly and explode as supernovae after only a few million years. These stars would enrich their surroundings almost immediately, seeding the next generation with oxygen, carbon, and nitrogen. That kind of accelerated enrichment isn't impossible, but it requires the earliest environments to favor the formation of huge, short-lived stars far more strongly than modern environments do. If this was common, it means the early universe may have produced light in giant, explosive waves rather than gentle steps. Webb's detection of early disks and spiral-like structures adds another complication. Classic theory argues that organized structures such as disks require long periods of gentle accretion, allowing gas to settle into a stable rotation. In young, chaotic environments filled with mergers, turbulence, and violent interactions, disk formation should be nearly impossible. Yet some early galaxies appear to have forms that resemble disks or show early hints of spiral behavior. That implies that gas flows in those galaxies were calmer or more coherent than expected. Something about the way matter fell into these halos may have allowed it to organize quickly rather than fragment into irregular shapes. This could point to early conditions that naturally promote angular momentum alignment, or it could indicate that some regions of space were unusually tranquil even at early times. Either scenario would force a revision to current theories of how galaxies acquire their shapes. Black holes provide yet another layer of intrigue. Several of the brightest and most puzzling early objects may be powered by growing black holes rather than stars. If early black holes were more common, or if they grew more quickly, they could dominate the energy output of young galaxies. That would make those galaxies appear brighter and more massive than they actually are. But for this explanation to work on a large scale, early black hole formation must have been far more efficient than we currently expect. Theories that propose massive black hole seeds, forming directly from collapsing clouds rather than stellar remnants, could support such rapid growth. If these seeds were common, and if gas in the early universe could funnel into them efficiently, they might grow to millions of solar masses in just a few 100 million years. That would change the entire story of how early galaxies formed, because black holes would contribute not only light, but also energy feedback that shapes gas flow, star formation, and overall galaxy evolution. Even the timeline of cosmic reionization may shift. The universe's transition from neutral hydrogen to ionized hydrogen, driven by the first stars and galaxies, was once thought to be a slow, extended process. But if early galaxies were more numerous, brighter, and more efficient at producing ionizing radiation, reionization could have happened faster or started earlier. That would influence everything from the temperature of early gas to the propagation of light through space. Webb is already finding evidence that reionization may have been patchier and more dynamic than expected, with bright early sources carving out bubbles of ionized gas long before the process was thought to be underway. If reionization began earlier or progressed more unevenly, it suggests that the early cosmos was less uniform and more structured. further challenging the idea of a simple, gradual emergence of complexity. The biggest implication of all is that the early universe may not have been dominated by slow hierarchical growth. Instead, it might have experienced a rapid, intense phase of galaxy formation that created a diverse population of objects in a short span of time. Some galaxies may have undergone extreme starbursts, while others grew around massive black holes. Some regions may have built disks early, while others remained chaotic. The early cosmos may have been more varied, less like a predictable sequence, and more like a rapid expansion of possibilities that settled into more stable patterns only later. This diversity could explain why Webb is finding objects across such a wide range of sizes, shapes, and chemical compositions at surprisingly high redshifts. At the same time, these implications don't necessarily require abandoning the standard cosmological model. They do, however, force us to update the details of how baryonic matter, ordinary matter, behaves within that model. Lambda CDM, the framework that describes the universe's expansion and structure growth, doesn't specify how efficiently gas turns into stars or how quickly black holes form. Those details are supplied by astrophysics, not cosmology. If early astrophysics played out differently than it does today, many of Webb's surprises could fit within the existing cosmological structure. That's why astronomers are cautious. The early giants might point to gaps in galaxy formation theory rather than cracks in the underlying cosmology. But it's also true that if the frequency, mass, and organization of these early galaxies continue to conflict with model predictions, even after careful follow-up, then cosmologists may need to revisit assumptions about early density fluctuations or the behavior of dark matter. Even slight changes to those early conditions could accelerate the timeline of structure formation. Some researchers are exploring whether dark matter might behave differently at small scales, or whether early fluctuations in the cosmic microwave background were slightly stronger than expected. These are subtle adjustments, not wholesale replacements, but they show how deeply the debate is now reaching. Ultimately, the early universe may turn out to be a far more dynamic era than previously assumed, an environment where matter assembled rapidly, stars formed explosively, black holes grew aggressively, and chemical complexity emerged with surprising speed. Webb has revealed a landscape where the first billion years weren't a gentle prelude, but a vibrant, energetic stage filled with unexpected actors. Our models did not anticipate this performance, but the universe rarely cares about our expectations. When scientists talk about uncertainty in the early universe picture, they're not just expressing caution for its own sake. They're acknowledging that Webb has dropped us into a part of cosmic history where even small interpretation errors can snowball into large conceptual misunderstandings. And because we're examining objects at the very edge of observability, every step, from measuring brightness, to estimating mass, to interpreting spectra, carries assumptions that might be perfectly reasonable in the local universe, but become fragile when pushed billions of years into the past. Understanding what remains uncertain is just as important as interpreting what appears solid, because the answers depend on separating what we truly know from what we're inferring out of necessity. One of the biggest uncertainties revolves around mass estimates. A galaxy's mass sets the stage for nearly every other interpretation: how fast it formed stars, how quickly it assembled, and how much gas it must have accreted. But mass is notoriously hard to pin down at these distances. The most common method involves measuring the galaxy's luminosity and then converting that luminosity into mass using models of stellar populations. That's straightforward when we understand what kinds of stars a galaxy contains. But for galaxies that formed only a few 100 million years after the Big Bang, we have no guarantee that their stars behave like the stars we use in our models. If early stellar populations were hotter, brighter, or more massive on average, their light could mislead us into thinking the host galaxy contains more total mass than it actually does. A galaxy that looks massive could be populated by unusually luminous young stars, rather than by a genuinely enormous number of them. Another source of uncertainty comes from dust. Dust absorbs starlight and re-emits it at longer wavelengths. In mature galaxies, this effect is well characterized, but in primordial galaxies, the dust content and composition are less predictable. If early galaxies contain more dust than expected, or if the dust behaves differently at high redshifts, it could distort the inferred ages, masses, and star formation rates. Observations might undercount older stars hidden behind dense dust lanes, or overestimate the brightness of star-forming regions because the dust re-radiates energy in the infrared. Since Webb observes primarily in infrared wavelengths, dust can either mask or mimic features depending on how it interacts with early radiation fields. Without precise knowledge of early dust physics, astronomers must rely on assumptions that might be slightly or significantly off. Redshift measurements themselves introduce another layer of uncertainty. While spectroscopic redshifts are reliable, many early candidates are initially identified through photometric redshifts, estimates based on how an object's light fits certain color patterns across multiple filters. In most cases, photometric redshifts are accurate enough to identify promising targets for follow-up. But at the extreme edges of the observable universe, where galaxies are faint and their spectra are dominated by only a few features, photometric methods can misclassify an object's age. A galaxy that appears to sit at redshift 12 might actually lie at redshift 8 after accounting for dust, unusual emission lines, or calibration uncertainties. Those differences translate into hundreds of millions of years in cosmic time. Even a small shift in redshift can dramatically alter the implications of that object's existence. Chemical measurements present another challenge. When we talk about metals in galaxies, oxygen, carbon, nitrogen, we're really talking about signatures in their spectra. These signatures are often subtle and, at extreme distances, they can be buried in noise or distorted by the spectral shape of the galaxy's stellar population. A line that appears strong might be boosted by an active black hole. A line that appears weak might be diluted by hot stars. Some early galaxies might contain unusual mixtures of population 3 stars, the first stars thought to be massive, metal-free and ephemeral. These stars could influence the overall color of the galaxy, making it appear more or less chemically enriched than it truly is. Without the ability to isolate the contributions from each type of star, chemical measurements must be treated with caution. Structural interpretations are also uncertain. Webb's resolution is impressive, but at the distances we're dealing with, even high resolution means working with only a handful of pixels. Determining whether a galaxy contains a disk, a bulge, a spiral arm, or a clump of star-forming regions often means examining tiny differences in pixel brightness. It's entirely possible that some features interpreted as organized structure are simply chance alignments of bright regions or gravitational lensing distortions. Lensing, in particular, can stretch or magnify a galaxy in ways that mimic coherent shapes. If the lens model is even slightly off, a galaxy that looks like an early spiral might actually be an irregular starburst, stretched into a deceptive arc. A deeper uncertainty lies in selection bias. Webb's earliest deep fields were chosen partly because they contained interesting foreground structures like galaxy clusters. These clusters act as lenses, magnifying distant sources and making unusual objects easier to detect. But this means we may be seeing an overrepresentation of extreme cases, galaxies that happen to fall behind magnifying lenses or that happen to be bright enough to stand out among thousands of faint, unremarkable objects. The early universe might not be filled with massive galaxies. It might be that Webb's initial surveys simply highlighted the rare ones first because they are easier to detect. Without broader surveys that cover random patches of sky, it's hard to know whether the early giants are common or exceptional. Another uncertainty comes from the way models handle star formation and feedback. In simulations, star formation occurs when gas reaches certain densities and temperatures, and feedback, energy from supernovae, stellar winds, and black holes, regulates how that formation proceeds. But these recipes are calibrated using local galaxies, not primordial ones. If the cooling channels in early gas worked differently due to different chemical compositions or background radiation fields, the thresholds used in simulations might misrepresent how quickly gas turned into stars. Similarly, if feedback was weaker or stronger in early galaxies, their growth histories could diverge from what models currently predict. These uncertainties don't invalidate models, but they do mean that conclusions about tension between models and observations must be drawn carefully. Even the cosmological implications remain uncertain. The Standard Model predicts how density fluctuations evolve, how dark matter collapses, and how fast halos should grow. If early galaxies appear too massive, one interpretation is that the model is wrong, but another is that our method of inferring halo mass from luminous mass is flawed. A bright galaxy doesn't necessarily sit in a correspondingly large halo. It might simply be incredibly efficient at turning gas into stars. Alternatively, if black holes contribute significantly to the observed brightness, the halo mass might be much lower than the luminosity suggests. Without direct measurements of halo masses at high redshift, something currently beyond our reach, it's difficult to know whether early galaxies challenge cosmology or just challenge galaxy physics. Another often overlooked uncertainty is the role of environment. Some early galaxies might have formed in unusually dense regions, cosmic neighborhoods where matter collected faster than average. If Webb's early deep fields happen to probe such regions, then the galaxies it finds might not represent the typical universe. They might instead reflect the most extreme environments, where rapid growth was possible and where the earliest large-scale structures began to assemble. Without mapping a variety of cosmic environments, we can't know whether the early giants reflect a cosmic norm or a cosmic outlier. And yet finally, there's the uncertainty that comes from novelty. Webb is observing territories where no telescope has gone before, using instruments that operate at the edge of technological limits. Calibration models will improve, noise will be better understood, and reduction pipelines will be refined over time. Measurements made in Webb's first 2 years might later be updated or corrected as teams refine their understanding of how its detectors behave under extreme conditions. This doesn't mean the early results are flawed, only that they are part of a long process of increasing accuracy. Just as Hubble's interpretations of distant galaxies evolved as calibration improved, Webb's extreme redshift discoveries will undergo continual refinement. All these uncertainties do not diminish the significance of Webb's findings. They enhance it. They highlight how much room there still is to learn, how much complexity remains hidden, and how careful we must be before rewriting the cosmic story. The early universe may indeed be more dynamic than expected, but the details of that dynamism are still emerging. The next few years will bring better spectra, cleaner measurements, more sophisticated models, and a wider range of observed environments. As the uncertainties shrink, the true nature of these early giants will come into sharper focus. Whether that picture aligns with the current cosmological model, modifies it, or expands it in surprising new directions, remains one of the most exciting open questions in modern astrophysics. When a field is moving this fast, it becomes tempting for observers and theorists alike to read too much into every new data point. Webb's images arrive, a handful of unusually bright or massive objects stand out, and immediately the conversation shifts to whether cosmology is broken, whether the universe behaved completely differently than we thought, or whether decades of theoretical work now need to be rewritten. It's a natural reaction. Surprise makes good headlines, and the earliest epochs of the universe carry a kind of gravitational pull on the imagination. But when scientists talk about the risks of over-interpreting early findings, they're not trying to dampen excitement. They're trying to keep the pace of discovery grounded in the reality of what we can and cannot conclude from preliminary evidence. The history of astronomy is full of moments where the first, most dramatic interpretation didn't hold up under deeper scrutiny. Not because the data were wrong, but because the conditions at the detection limits can trick even careful observers. One of the biggest risks comes from the sheer novelty of the territory Webb is exploring. We have no prior imaging or spectroscopy at comparable resolution or sensitivity for this era of the universe. That means there is no training set, no established baseline to compare against. When Hubble pushed to higher redshifts, it could still rely on decades of experience with optical imaging. Webb, by contrast, is venturing straight into wavelengths and distances where the relationship between light and underlying physics is still being mapped. Features that might seem unusual could later turn out to be typical once we have larger samples. A galaxy that looks impossibly structured for its age might represent a statistical outlier rather than a paradigm shift. Until we gather more observations, it's difficult to know whether we're seeing a pattern or simply the standout cases that rise above the detection threshold. Another danger comes from focusing too quickly on the most dramatic explanations. If a galaxy appears too bright or massive, it's tempting to conclude that our models must be wrong. But the most straightforward explanation is often that the object has properties or complexities that are difficult to capture with simple models. Intense starburst phases, contributions from black holes, unusual dust geometries, or gravitational lensing effects that distort its true size or shape. This isn't to dismiss the possibility that something deeper is happening. It's just a reminder that astrophysics rarely offers simple, single-variable answers. Observations at extreme distances often involve several overlapping processes that must be untangled carefully before reaching a bold conclusion. A related risk is collapsing a broad range of observations into a single narrative. Webb has discovered early galaxies that appear massive, early galaxies that are chemically developed, early galaxies with surprising structure, and early galaxies that simply don't match expectations. It's natural to try to link all of these into one grand explanation. Maybe the entire universe formed structures faster than expected. Maybe the standard model needs revision. Maybe something exotic was happening in the first billion years. But there's no guarantee that all these anomalies share a common cause. In fact, they might reflect a diversity of early environments and processes. One galaxy might be bright because of an active nucleus. Another might be massive because of rapid gas inflow. Another might appear chemically enriched due to a brief but intense burst of star formation. Treating them as symptoms of one underlying flaw in our theories exaggerates the degree of tension and risks, oversimplifying what is likely a far more intricate story. Observational bias plays an especially subtle role in this era. Webb has looked deeply into only a tiny fraction of the sky, and these early fields often include gravitational lenses, massive clusters that magnify distant objects. This makes it easier to detect the most extreme galaxies because lensing amplifies their brightness. But it also means we may be missing the full population of ordinary early galaxies. If you survey only the regions where lensing makes dramatic objects visible, you'll naturally form the impression that the early universe is filled with shockingly massive or bright structures. As Webb expands its deep field program to include non-lensed regions, the distribution of observed galaxy types may shift. A proper understanding of the early universe requires accounting for the selection effects introduced by the very tools that make these discoveries possible. There is also the risk of interpreting theoretical models too rigidly. Cosmological simulations, even the most advanced ones, rely on approximations. They model dark matter with high precision, but baryonic physics, the physics of ordinary matter, is far more complex. Star formation, gas cooling, feedback from supernovae and black holes, and turbulence all require simplifications. These subgrid models are calibrated using observations of relatively nearby galaxies. When those models are extended into the early universe, they may not reproduce the full range of possible behaviors. If a simulation predicts that no galaxy should exceed a certain mass at a given redshift, that prediction isn't a fundamental law. It's a consequence of the assumptions built into the code. When observations exceed those predictions, it might signal the need to refine the models, rather than the need to discard the underlying cosmology. Another pitfall involves overconfidence in photometric redshifts. These methods are remarkably powerful, especially with Webb's wide wavelength coverage, but they can still misclassify unusual objects. A galaxy with strong emission lines can trick photometric models into thinking it lies farther away than it does. A dusty galaxy at moderate redshift can mimic the colors of a pristine galaxy at extreme redshift. If 2 or 3 such misclassifications slip into a sample, they can skew the inferred distribution of massive or bright galaxies. Until spectroscopic redshifts are obtained for the most extreme candidates, any claims about how many galaxies existed at a given early time must remain provisional. There's also a risk of confirmation bias creeping in from both observers and theorists. Once a few papers claim that the early universe contains unusually massive galaxies, it becomes easier for future studies to interpret ambiguous data in ways that support that idea. If a galaxy's mass could be either relatively modest or extremely high depending on model choices, the more dramatic interpretation might attract more attention. Over time, this can create the illusion of a coherent trend even if the underlying data are more scattered. The best defense against this is transparent reporting of uncertainties, careful comparison of alternative models, and expanded samples that dilute the influence of outliers. A different kind of overinterpretation comes from the tendency to take the earliest possible redshift estimates as the final word. When Webb detects a candidate galaxy that appears to sit at an astonishing redshift, say redshift 15 or above, the excitement makes headlines. But many of these extreme claims soften after detailed analysis. Some objects originally thought to be among the earliest galaxies ever seen later turn out to be at more moderate distances. This pattern is not a failure. It's the normal scientific process of refining estimates as better data arrive. But if early claims are treated as definitive, they can mislead both the public and the research community about the severity of tension with existing models. It's also important to remember that the early universe was likely messier and more heterogeneous than simple models imply. Cosmologists often speak about the average timeline of structure formation, but the universe is not an average place. Some regions form halos earlier, some later. Some areas see rapid gas inflows, others remain relatively quiet. If Webb happened to observe a region that experienced an early burst of structure formation, that region might contain unusually massive galaxies, even if most of the universe at that time did not. Without surveying a wider range of cosmic environments, we can't know whether Webb's first deep fields are representative or not. Jumping to conclusions based on a tiny window into the cosmos risks constructing theories around what might be cosmic coincidences. Overinterpreting findings can also lead to unnecessary tensions between observational teams and theorists. Theorists might feel pressured to adjust models prematurely, while observers might feel compelled to frame results in the most dramatic terms to attract attention. But science works best when both groups have room to explore without rushing to resolution. The early Webb results should motivate deeper investigations, not force model revisions before the full dataset is in hand. A premature narrative, whether it suggests that galaxy formation models are failing or that everything fits perfectly, can lock the field into assumptions that later data might contradict. Public communication adds another layer of complexity. Webb's discoveries are genuinely exciting, and the public response has been enthusiastic. But when headlines suggest that everything we know is wrong, or that Webb breaks the Big Bang, the conversation shifts from curiosity to sensationalism. This creates pressure on researchers to either defend the established model more aggressively or push alternative interpretations harder than the data warrants. In both directions, nuance is lost. The field risks being pulled into debates shaped more by dramatic storytelling than by careful accumulation of evidence. Finally, the risk of over-interpretation grows when the pace of discovery outstrips the pace of analysis. Webb's data arrive in huge quantities. Teams scramble to process, classify, and interpret them. Preprints appear rapidly, sometimes before full peer review. Other teams respond with counter-analyses based on their own modeling assumptions. In such a fast-moving environment, it's easy for small uncertainties to snowball into large disagreements. The solution is time. Time for follow-up observations, time for teams to check one another's work, time for models to be updated, time for independent surveys to confirm or challenge initial findings. None of this is meant to downplay the magnitude of Webb's discoveries. They are forcing astrophysicists to rethink early star formation, early chemical enrichment, and early structural organization. But the extent of the revision remains an open question. By avoiding overinterpretation, researchers keep the focus on what the data truly show and allow the evolving story of the early universe to emerge naturally, rather than bending the data to fit a premature narrative. What we have now is an extraordinary first draft of the universe's opening chapters. A draft full of unexpected characters and fast-moving events. But it's still a draft. The next steps involve refining the text, filling missing pages, correcting early misreadings, and understanding the context behind each surprising line. Only then can the story be told with confidence. In the wake of Webb's observations, the scientific community has found itself in one of the most animated, intellectually charged debates in modern cosmology. It isn't a clash defined by entrenched camps or ideological divides. Instead, it's a conversation fueled by data arriving from a frontier that no telescope has reached before, a frontier that pushes every model, every assumption, every computational trick, and every theoretical intuition to its limits. Researchers are trying to figure out how much of what Webb reveals is genuinely new physics and how much reflects the natural complexity of an era we have barely begun to observe. Within that ambiguity lies the heart of the debate. Are we witnessing the universe behaving exactly as it should, just in ways that simulations have yet to capture? Or are we seeing signs that the foundational framework underpinning our understanding of cosmic evolution might need revision? One of the central points of discussion concerns the nature of the massive early galaxies that Webb keeps identifying. The question is not simply whether these galaxies exist, they clearly do, but what they are, physically and phenomenologically. Some teams argue that the observed brightness and compactness of these objects imply exceptionally high stellar masses, possibly rivaling contemporary galaxies only a few 100 million years after the universe began. Others suggest that the mass estimates might be inflated by assumptions built into the modeling process. For example, if early stars formed with different mass distributions, or if extremely young stellar populations dominated the early galaxy phases, then conventional mass-to-light ratios may no longer apply. This means many galaxies that appear impossibly massive could be much lighter, simply glowing with a type of radiance our models aren't fully calibrated to interpret. The debate hinges on photometry, stellar population synthesis, and what researchers think the first generations of stars actually looked like. Another major axis of disagreement revolves around the interpretation of chemically mature spectra in these early galaxies. Webb has detected oxygen, neon, and other heavy elements in galaxies from epochs when heavy element production should have barely begun. Some scientists view this as evidence that the first stellar generations formed and died much faster than expected, enriching their galactic environments with metals in astonishingly short timescales. Others argue that the interpretation of certain lines as metal signatures might be confounded by extreme ionization conditions or unexpected contributions from compact black holes. Still others entertain the possibility that these galaxies represent a rare but not impossible subset of the early environment, regions where star formation was so intense that chemical enrichment occurred in bursts rather than in the slower, more predictable patterns observed later. These differing perspectives reflect the uncertainties inherent in interpreting spectra from galaxies so distant that every photon has traveled more than 13 billion years to reach us. There is also intense discussion about the large-scale structure implications of these early discoveries. If galaxies of such mass and complexity existed so soon after the Big Bang, it implies that the underlying dark matter halos must have formed earlier and collapsed faster than many models predict. Some researchers argue that this represents a genuine tension with the lambda CDM model, suggesting that either the power spectrum of primordial fluctuations needs adjustment, or that the nature of dark matter may not be exactly as the standard model assumes. Others counter that rare peaks in the density field could naturally produce early forming halos, and that Webb may simply be sampling regions where such early peaks occurred. This argument is especially provocative, touching on deep questions about the initial conditions of the universe and whether small tweaks to the primordial fluctuations could resolve the seeming inconsistencies. The question of whether simulations are failing or merely incomplete is another focal point of the current scholarly discourse. Several simulation teams are racing to update their models with more detailed baryonic physics and more flexible star formation prescriptions. These updated simulations can sometimes reproduce massive early galaxies within the lambda CDM framework, especially when extreme conditions, such as highly efficient gas inflow, are included. But critics point out that tuning simulations to match new data risks, introducing biases. Once you allow enough free parameters, any model can be coaxed to match observations. The real challenge is determining which physical processes are truly at play and which are merely computational crutches used to force consistency with the latest observational surprises. This tension between realism and flexibility in modeling lies at the heart of many academic exchanges, often revealed in the comment sections of preprints and the spirited debates at conferences. A related debate concerns the true nature of the 330 strange objects identified in one widely circulated study. Some astronomers argue that many of these objects might be black hole-dominated systems rather than typical star-forming galaxies. If that is true, it could fundamentally reshape our understanding of the early universe. Instead of needing to explain how galaxies formed so fast, we might need to explain how black holes grew so fast, which is an equally daunting challenge, but one that might invite different solutions. Critics of this view maintain that without deep spectroscopic confirmation, classifying these objects as black hole-dominated is premature. Others suggest that the population likely contains a mix, some extreme galaxies, some active nuclei, some misidentified interlopers. This debate showcases the challenge of interpreting photometric catalogues at the limits of detectability, where multiple astrophysical scenarios can produce similar observational signatures. The spiral galaxy discovered at surprising cosmic timescales has sparked its own strand of debate. A galaxy displaying beautifully ordered spiral arms only about 1.5 billion years after the Big Bang challenges conventional ideas about when organized structure could emerge. Some researchers argue that this implies the early universe was more dynamically mature than previously thought, with cold gas streams and stable disk structures forming earlier than predicted. Others caution that a single example, striking though it may be, does not rewrite the timeline of structural evolution. Spiral galaxies might be rare outliers, the cosmic equivalent of early architectural marvels rather than the norm for that epoch. The debate hinges on whether further examples will be found, and whether those examples will display similar levels of organization or represent different evolutionary pathways. Questions about feedback, how energy from stars and black holes shapes galaxy growth, are also central to current discussions. In modern galaxies, feedback helps regulate star formation, preventing runaway growth. But in the early universe, feedback might have been less effective, allowing galaxies to rapidly build mass before winds and radiation carved out channels in the gas. Some theorists argue that extremely inefficient feedback in the early epoch could explain the surprising masses of the earliest galaxies. Others counter that such weak feedback would create problems for explaining other observations, such as the timeline of cosmic reionization or the distribution of metals. Because feedback is notoriously difficult to simulate, these debates often take on a philosophical tone. How do you model processes that even in nearby galaxies remain imperfectly understood? There is also discussion around the nature of the initial mass function of early stars. If the earlier stars formed with disproportionately high masses compared to later generations, they would shine brighter, die faster, and enrich their surroundings more rapidly. This could help explain both the extreme luminosities and chemical signatures detected by Webb. Supporters of this view point to theoretical models of population 3 stars, which predicted exactly such a mass distribution. Skeptics note that while the idea is appealing, direct evidence for these star populations remains elusive. Without clearly identifying the signatures of true first-generation stars, it's difficult to determine whether the early galaxies Webb sees are powered by exotic stellar populations or by more familiar processes scaled up to extreme environments. The debate about whether Webb's discoveries challenge the standard cosmological model is perhaps the most visible and contentious. Some researchers believe that the tension is real enough to suggest that something fundamental is missing. They point to other anomalies, such as early quasars with billion solar mass black holes, as additional evidence that early structure formed too quickly under conventional assumptions. Others maintain that the standard model remains robust and that the anomalies reflect the natural variance in early cosmic regions or limitations in current simulations. Both sides agree on one thing: the data are remarkable and require thoughtful interpretation. But the conclusions drawn from the data vary widely, reflecting different levels of confidence in simulations, different modeling assumptions, and different theoretical starting points. Even the question of how to interpret Webb's sharp, infrared-rich imaging plays into these debates. Webb's instruments reveal stars and dust structures that were invisible to Hubble, making early galaxies appear both more complex and more easily analyzable. But this also means that comparisons with earlier models, which were built using lower resolution, shorter wavelength data, may not always be fair. Some researchers argue that Webb is not showing galaxies that are fundamentally different from what models predicted. Instead, it is revealing complexities that were always there but previously undetectable. Others counter that even when adjusting for new visibility, the observed masses and structures still exceed expectations. Underlying all these debates is a shared recognition that the early universe is turning out to be more dynamic, diverse, and complex than anticipated. What scientists disagree on is the degree of revision required. Are we dealing with minor adjustments to existing models, refinements of assumptions that were always approximations? Or are we on the cusp of a deeper shift, one that could reshape our understanding of cosmic growth, dark matter behavior, or primordial conditions? What makes the current moment so compelling is that no single interpretation has claimed dominance yet. Instead, the field is in a state of fertile uncertainty. Every new dataset can strengthen one argument while complicating another. Every new simulation can show how small tweaks resolve one mismatch, yet create a new tension elsewhere. Every new spectrum from an ultra-distant galaxy can either reinforce an emerging pattern or disrupt it. The debates are not signs of crisis, they are signs of a healthy scientific process responding to unprecedented data. Webb is expanding the empirical foundation on which cosmology stands, and scientists are racing, collaboratively, competitively, and creatively, to build interpretations strong enough to stand atop it. The consensus, if one exists, is this: the early universe was not the slow, steady, orderly place that older models implied. It was fast, fierce, varied, and perhaps more efficient at building complexity than anyone predicted. But exactly how fast, how fierce, and how efficient remains the subject of ongoing debate, a conversation that Webb continues to fuel with every new observation. When you step back from the details, the spectra, the mass estimates, the debates about feedback efficiency, the uncertainties in modeling, the questions about dark matter halos, what Webb has really done is force us to reconsider the pace at which complexity can appear in a young universe. For decades, the intuition shared across cosmology was that structure took time. It wasn't just a rule of thumb, it was woven into the underlying physics. Gas has to cool before it can collapse. Stars need to form, burn, and die before heavier elements can appear. Galaxies need to merge, interact, and build up mass over long cycles. And dark matter halos, the cosmic scaffolding that everything rests on, must gradually attract matter before anything interesting can happen inside them. All of that created an expectation, a slow cosmic dawn, a gentle ramp-up from simplicity to complexity. Webb is revealing a universe where that ramp-up looks more like a staircase with some surprisingly tall steps. Those early massive galaxies, the chemically enriched systems only a few 100 million years after the Big Bang, the structured disks, the spiral patterns, the compact quasar-like candidates, and even the hundreds of strange objects that don't fit into the neat categories we use today. They all point toward a universe that got busy faster than we thought. Not because the physics is broken, but because the universe seems to have used that physics in ways we hadn't fully accounted for. There is an elegance to that idea. The laws of nature aren't failing. We are just finally seeing them play out under conditions we've never observed directly. It's like reading the first chapters of a book you've only known by its summary. You thought you understood the plot, but the details turn out to be far richer. A key part of the takeaway is that the early universe might have had pathways for rapid growth that were always possible but extremely difficult to simulate. Back when only Hubble data was available, theorists and simulators were working with limited information about early star-forming clouds and the small, faint galaxies that populated cosmic dawn. With weaker data, you naturally end up building models that emphasize the average case, not the most extreme scenarios. But Webb's results highlight those extremes, the overachievers of the early cosmos. They may not represent typical galaxies, and that's completely fine. A handful of extraordinary objects is still enough to reveal that our assumptions about the average case need refining. If a few galaxies can kick off star formation feverishly enough to build 100 billion solar masses of stars in less than 1 billion years, or accumulate enough metals to light up the spectrum with oxygen and neon lines at an age when the universe was barely out of its infancy, then the early cosmic environment must have been more flexible and more diverse than expected. At the same time, the discoveries remind us that cosmic evolution is not a single universal story. It's a tapestry woven from countless threads, each representing a region with its own density, temperature fields, dark matter distribution, and merger history. What Webb sees at extreme distances are snapshots of these threads, some of them ordinary, some wildly atypical. These snapshots challenge the idea that early galaxies were uniformly small, chaotic, and chemically simple. Instead, they suggest a spectrum of outcomes, some remaining tiny and irregular, others exploding into maturity far ahead of schedule. In that sense, Webb is not contradicting cosmology. It is enriching it by showing just how varied the early environment actually was. Another important part of the takeaway is the way Webb blurs lines between categories that once seemed clear. Historically, we separated early galaxies into phases: primordial clouds, tiny proto-galaxies, gradual growth, steady enrichment. Now the boundaries seem fuzzier. Is a chemically enriched galaxy at redshift 14 a freak outlier or part of a broader class? is an early compact object powered primarily by star formation or by a rapidly growing black hole? And how easily can those scenarios be disentangled? Even the spiral galaxy found just 1.5 billion years after the Big Bang forces us to rethink how orderly cosmic structure can become while the universe is still young. These categories, star-forming galaxies, quasars, spirals, mergers, might not have had the clear evolutionary sequencing we imagined. Instead of a neat timeline, we may be looking at overlapping processes that sometimes run ahead, sometimes lag behind, and sometimes take unexpected shortcuts. One of the deeper implications of all these discoveries is that cosmic evolution might not operate under a single speed limit. In some regions, gravity, gas inflows, and dark matter halos may have aligned in ways that accelerated growth dramatically. In other regions, growth might have been sluggish. Webb shows us that the early universe was filled with pockets of opportunity, places where conditions briefly lined up to allow galaxies to form stars at unprecedented rates. These pockets are scattered across the sky like tiny laboratories where nature experimented with fast-track galaxy formation. The existence of such laboratories doesn't undermine cosmology, it broadens our understanding of what's possible. There's also a philosophical dimension to the overall takeaway. Cosmology has always balanced two narratives, the universal and the particular. The universal story is the one written in the equations, the expanding metric, the cooling plasma, the formation of structure guided by cold, dark matter. The particular story is the one written in light, each galaxy, each star cluster, each black hole presenting its own biography. For years, models provided the universal story, and observations provided a limited number of particular stories. Webb has flooded us with new biographies, and some of them are written in dialects we didn't expect. This tension between the universal and the particular is not a flaw, it's the dynamic that drives science forward. What's especially exciting is that Webb is not just uncovering anomalies, it's offering a chance to unify these discoveries into a deeper understanding of how the universe behaves under extreme conditions. Every time a spectrum comes back with heavy elements earlier than predicted, it teaches us something new about star life cycles at near-zero metallicity. Every time a galaxy appears far more massive than expected, it forces theorists to revisit the interplay of gas cooling, halo growth, and star formation efficiency. And every time an object refuses to fit neatly into existing categories, it hints at new astrophysical processes, or new combinations of old ones, that we haven't appreciated fully. This is not a story about disproving the standard model, though some headlines and commentaries occasionally lean in that direction. It's a story about refinement, about growth, about discovering that a model built from limited observational constraints is now being asked to describe a universe far richer and more varied than we once realized. The cosmological framework remains strong, but its details, especially the messy, complex physics of galaxy formation, are being rewritten in real time. Webb has reminded the field that galaxy formation is not governed by a simple checklist of steps, but by a dynamic interplay of processes that can produce extraordinary results under the right conditions. Another major takeaway is that these discoveries are not isolated curiosities. They ripple outward into multiple domains of astrophysics. If early galaxies were building stars faster than expected, that affects our understanding of cosmic rionization, how the first stars and galaxies transformed the intergalactic medium. If early black holes were growing faster than expected, that affects models of quasar formation, feedback, and the growth of supermassive black holes. If early chemical enrichment happened quickly, that affects predictions about the distribution of elements in the oldest surviving stars in our own galaxy. Webb isn't just challenging timelines, it is steering entire subfields into new territory. The results also highlight the importance of direct observation. For years, simulations predicted that the first galaxies would be faint, irregular, and modest in mass. That was a reasonable conclusion based on the data available at the time, but science moves forward when data challenges expectations. Webb's deep fields, infrared spectra, and sharp imaging are doing exactly that. They are pushing the observational boundary so far back that our models, built in a different era, are struggling to keep up. The models will catch up, they always do, but only because the data force them to. Perhaps the most important takeaway is the sense of possibility these discoveries create. Webb has given us access to an era when the universe was only a few % of its current age, and what we see there is astonishingly diverse. It's no longer just a dim, distant chapter of cosmic history. It's a bustling landscape filled with bright galaxies, heavy elements, massive halos, active black holes, complex structures, and unexpected overachievers. The early universe isn't a quiet prologue. It's the explosive opening scene of a story that turned out to be far more dramatic than the summary we were handed. The deeper message behind all of Webb's surprises is that the universe has always had the capacity for rapid creativity. It didn't wait billions of years to get interesting. It was interesting almost from the start. That doesn't break cosmology. It enriches it. It adds texture to the timeline, complexity to the environments, and nuance to the processes we study. And it reminds us that our theories are tools, not verdicts. When new data arrives, the tools must adapt. That's why these discoveries matter. They are not puzzles to be solved for their own sake. They are windows into how nature behaves when conditions are extreme. They show us that the universe's earliest moments weren't ruled by uniformity and slow progression, but by rapid growth, dramatic contrasts, and bursts of complexity that we're only now beginning to understand. Every new observation pulls another thread from the tapestry, revealing patterns we didn't know were there. As Webb continues to peer deeper, it will almost certainly uncover more surprises, some that resolve current mysteries, others that create new ones. But that's exactly how it should be. A telescope capable of seeing the universe at such early stages should change our understanding. If it didn't, it wouldn't be doing its job. The strange thing about this moment in astronomy is that it doesn't feel like we've reached an answer. It feels like we've reached a starting line. Everything Webb has shown us so far, the unexpectedly massive early galaxies, the chemical richness long before it should have existed, the tightly wound spirals, the compact and luminous objects that defy easy classification, the possible early black hole overachievers. None of it feels final. These discoveries read more like the first clues in a much larger mystery than a solved chapter. If anything, the more Webb reveals, the more it suggests that the early universe holds layers of complexity we've barely begun to peel back. And the telescope is still young, still warming into its full capacity, still aiming at regions of the sky we haven't scrutinized with this level of detail before. It raises an obvious question. If this is what we've found already, then what lies just beyond the edges of its deepest fields? One of the biggest open loops comes from the simple fact that Webb has only stared deeply into a handful of tiny patches of sky. These pencil beam surveys represent an absurdly small fraction of the full universe, yet they're already filled with objects that are pushing theoretical limits. If even one of these fields contains multiple galaxies that formed faster than expected, how many must exist across all of cosmic dawn? It's entirely possible that what we're seeing is the tip of an iceberg, an early population of galaxies that is both more common and more diverse than anyone predicted. If Webb expands its deep field program and begins mapping larger areas with the same precision, the census of these early giants may grow dramatically. Some theorists think the next few years will reveal not dozens but hundreds of extremely early, chemically evolved galaxies, a population large enough to force major adjustments in how we model the first billion years of cosmic evolution. Another direction Webb is pushing toward involves capturing more detailed spectra of these distant objects. Photometric redshifts can be misleading. They can hide multiple astrophysical scenarios under the same color profiles. Spectra, on the other hand, provide fingerprints, elementary clues about temperature, density, metallicity, star formation rates, black hole activity, and the ages of stellar populations. The more spectra we gather from these early galaxies, the more we'll learn about whether they truly contain heavy elements earlier than expected, or whether their light is being shaped by extreme conditions that mimic metal-rich signatures. In the next few observing cycles, Webb will devote more time to high-resolution spectroscopy at extreme redshifts. If the early universe really was producing heavy elements at a breakneck pace, the spectral lines should confirm it. If instead the early galaxies are being powered by combinations of star formation and black hole activity that we haven't fully modeled, that will become clear as well. Either way, the incoming data will refine our theories, cutting away some of the uncertainties that currently fuel debate. There's also the mystery of the compact, ultra-bright objects that might be the seeds of supermassive black holes. Webb has already detected candidates that look like they could be rapidly growing black holes just a few 100 million years after the Big Bang. The existence of such early black holes is challenging enough, but the real question is how common they are and what their growth histories look like. If future observations reveal that these compact powerhouses are everywhere, that they were a normal product of early star formation, then we may need to rethink how the first black hole seeds formed. Did they come from the collapse of enormous primordial stars? Were they born from dense stellar clusters that collapsed under their own gravity? Or is there some other pathway, like the direct collapse of gas clouds in regions where cooling was suppressed? Webb doesn't yet have the sample size to answer these questions, but that will change as more ultra-high redshift objects receive follow-up observations. Once we know how many early black holes existed and how fast they grew, we'll have a much clearer picture of the engines that drove early galaxy evolution. One of the most exciting open loops involves the first generation of stars, population 3 stars, the theoretical giants made of pure hydrogen and helium. They have never been directly observed, but their fingerprints may be hiding in some of Webb's early spectra. These stars are thought to have been massive, luminous, and short-lived, producing the first heavy elements that seeded the next waves of star formation. If Webb can identify environments where these stars recently lived or catch their chemical residues in early galaxies, it would open an entirely new chapter in astrophysics. Several teams are already studying galaxies at redshifts above 12, hunting for unusual spectral signatures that could mark the presence of extremely low metallicity or metal-free stellar populations. It's a bit like looking for the ashes of a fire that burned out billions of years ago. If future data shows clear signs of these first stellar generations, it would not only confirm long-standing theories, but also reveal how quickly the universe transitioned from its primordial state to one filled with complex chemistry. Another open thread is how these early discoveries connect to cosmic rionization, the era when ultraviolet light from early stars and galaxies transformed the intergalactic medium. Observations from WMAP and Planck suggested a broad timeline for rionization, but they didn't reveal which sources drove the process. Webb may be able to identify the specific galaxies responsible. If the early universe contained more massive, luminous galaxies than expected, then these galaxies may have contributed far more ionizing photons than earlier models assumed. The coming years of Webb observations will likely refine the rionization timeline, showing whether the process was driven by many small galaxies, a smaller number of overachievers, or a mix of both. Understanding this transition is crucial because it marks the point where the universe became transparent to ultraviolet light and allowed structure to develop more freely. One of the gaps still waiting to be filled concerns how early galactic environments interacted with their dark matter halos. Simulations often treat dark matter as a static background, but in reality, the baryonic and dark components influence each other. The early galaxies Webb discovered seem to have grown so quickly that they must have lived in dense halos with unusual collapse histories. But what made those halos special? Were they seeded by primordial fluctuations that were stronger than average? Did they form earlier than typical halos of similar mass? And are these early halos common enough to fit comfortably within the lambda CDM framework, or do they force adjustments in the power spectrum or dark matter properties? Webb alone cannot answer these questions, but it can provide a map of where and when these early galaxies formed. Combined with upcoming gravitational lensing surveys, future data may reveal whether these extreme halos were rare exceptions or signposts of new physics. Webb also hints at the possibility that we might find entirely unexpected kinds of objects, systems that fall outside the familiar categories of galaxies, quasars, mergers, or clusters. Several candidates already show combinations of brightness, compactness, and spectral features that don't align neatly with known types. These could turn out to be unusual stages of galaxy evolution, or they could represent transitional phases that haven't been observed before. There's even a chance that some might reflect astrophysical processes that played major roles early on, but later became rare or extinct. For example, regions of ultra-dense gas collapse could produce starburst cores capable of forming millions of stars in extremely short bursts. Or black holes might temporarily dominate the energy output of a galaxy before settling into a quieter phase. If Webb continues to detect objects that defy our classification schemes, astronomers may need to expand the vocabulary of galaxy formation. Another future pathway involves gravitational lensing, which can magnify extremely distant galaxies that would otherwise be too faint to detect. Webb has already used lensing to reveal some of the earliest known galaxies, but deeper and more systematic lensing surveys could uncover even fainter and more distant objects. This opens the possibility of detecting galaxies at redshifts well beyond 15, maybe even approaching 20, corresponding to times just 150 to 200 million years after the Big Bang. If such galaxies exist, and Webb is capable of finding them, it would push our observational boundary into an era so close to cosmic dawn that even our best theories are tentative. Finding galaxies this early would reveal whether the universe formed its first structures almost immediately, or whether the current discoveries represent the upper tail of a broader distribution. Of course, Webb is only one piece of the future observational puzzle. The next generation of ground-based telescopes, the Extremely Large Telescope, ELT, the Giant Magellan Telescope, GMT, and the 30-meter telescope, TMT, will offer complementary views with far larger mirrors and powerful spectrographs capable of dissecting early galaxies in ways Webb cannot. These observatories will be able to zoom into individual regions within distant galaxies, measuring metallicity gradients, resolving small star-forming clumps, and tracing outflows and inflows of gas. They will help determine whether the early giants formed smoothly, in orderly disks, or through chaotic mergers and bursts. Combining Webb's deep infrared view with these upcoming high-resolution instruments will be like switching from reading headlines to reading full articles. Even more transformative could be the next generation of space telescopes. Concepts like the Habitable Worlds Observatory, LUVOIR, or Origins Space Telescope would push far beyond Webb's capabilities, offering higher sensitivity, broader spectral coverage, and even sharper resolution. Some of these mission concepts aim to detect the chemical fingerprints of life on distant exoplanets, but they would also revolutionize our view of the early universe. With larger mirrors and next-generation detectors, they could spot galaxies at even earlier times, measure faint spectral lines that Webb cannot reach, and map out the full distribution of early structures across larger swaths of the sky. These mission ideas are still years away, but Webb is laying the foundation for them. The puzzles we're uncovering now will shape the priorities of those future observatories. In the end, the biggest open loop might be the simplest. We don't yet know how surprising the early universe truly is. Webb has shown us that it's more complex, more dynamic, and more diverse than models anticipated. But we haven't seen enough to know whether the current anomalies are unusual outliers or the first hints of a broader pattern. We don't know how far back the timeline of galaxy formation truly stretches, how rapidly the earlier stars enriched their surroundings, how common early black holes were, or whether some of the first galaxies followed evolutionary paths we haven't imagined yet. We're standing on the threshold of an era where each new deep field, each new spectrum, each new ultra-high redshift candidate carries the potential to shift the narrative. That's the real teaser. Webb is not done surprising us. It has the sensitivity to keep pushing the boundary of the observable universe, and every few months, it delivers something that forces scientists to revise, rethink, or reimagine what early cosmic evolution looked like. It's not that the universe is breaking rules, it's that the rules are more flexible, more nuanced, and more inventive than we assumed. We're only now starting to appreciate that creativity. So when you take a step back and look at the whole picture, the massive galaxies appearing too early, the chemically mature systems that shouldn't yet have had time to enrich themselves, the structured spirals forming long before the cosmos should have allowed such order, the compact objects that may be hyper-growing black holes, and the sheer number of strange candidates cropping up in Webb's deep fields, you start to realize something important. The early universe wasn't the simple, quiet place our textbooks once painted. It wasn't a slow simmer. It was a cosmic pressure cooker, a forge of rapid growth, of fierce light, violent change, and unexpected structure. It was a universe in a hurry. And maybe that's the real legacy of the James Webb Space Telescope. It didn't just reveal new objects. It didn't merely push the boundary of how far we can see. It exposed a universe that refuses to fit neatly inside our equations. A universe that doesn't behave as predictably as we assumed. A universe that, at its earliest moments, was more ambitious than we ever imagined. But here's the thrilling part. We're still at the very beginning of Webb's lifespan. The telescope is healthy, stable, cold, and performing better than expected. It hasn't even completed a true full-sky deep survey. It hasn't yet collected the volume of spectra needed to stitch together a complete early cosmic census. The next few years will be where the shockwaves really hit. As new data arrives, astronomers will refine their models, argue, revise, test, break, rebuild, and ultimately uncover a clearer picture of how the first light structures truly formed. And who knows what waits beyond that? Maybe we'll find galaxies at redshift 18 or 20. Maybe we'll find the chemical fingerprints of the very first stars. Maybe we'll discover that black holes were shaping galaxies from the very first moments. Or maybe, and this is the part no one says out loud, maybe we'll find something so unexpected, so out of left field, that it forces a rewrite not just of galaxy formation, but of our understanding of the universe itself. Because if there's one thing the James Webb Space Telescope has proven, it's this: the universe still has secrets. And we are only now learning how to ask the right questions. If you've enjoyed this deep dive into the early universe and the mysteries Webb is uncovering, make sure you subscribe, hit the bell, and stick around, because this story is nowhere near finished. In the coming months, as new Webb data drops, we're going to explore the discoveries that could reshape cosmology all over again. The early universe might be far away, but the next surprise, that's coming soon. Thanks for watching, and stay curious because the cosmos is just getting started.